Okay, this is an excerpt from the upcoming insane EVM Opcodes assembly formal verification course that's going to come out on Cyfrin Updraft very soon. This is a 4.5 hour excerpt of that course. And in this video, you are going to learn how to go to Etherscan, check any smart contract that isn't even verified, go down to this section down here where it's just raw hex data, and be able to understand what all these opcodes are doing and what this contract is doing. How are we going to do that? Well, we're going to take this smart contract and we're going to rewrite it completely in this language, Huff, which is essentially like writing in opcodes. And in doing so, you are going to become a gas optimization wizard. You're going to be able to take any compiled Solidity smart contract and deconstruct it opcode by opcode. No longer will this hex data mean nothing blankness to you. You will be opcode literate. Then we're going to introduce you to inline assembly, or the YUL programming language. And you're going to rewrite this smart contract again with inline assembly. And then you're going to rewrite it again in pure YUL. And then finally, we're going to crank it up a notch. You're not just going to rewrite this smart contract in opcodes. You're also going to rewrite this smart contract completely in Huff, meaning you will have essentially written it in hex data yourself. Having this knowledge will make you the savant. You, one of the very few people who really understands gas optimizations at the lowest, most fundamental level. Additionally, you are going to gain the knowledge needed to be able to audit or do security reviews on these inline assembly chunks of code in smart contract, or you can actually add them to your smart contracts, actually knowing what they do. This will unlock a whole new level of sophistication for either your smart contract developing or auditing / security prowess. And like I said, the entire course that will teach you all of this, plus formal verification, plus even more assembly, plus how to do differential testing and more, will be on Cyfrin Updraft for you to learn. Whether you are a complete beginner or advanced smart contract developer or security researcher, that is your Bible for knowledge. So let's talk about the prerequisites for watching this video. We work with a lot of stuff in this video. We assume you're working with VS Code or some type of text editor. We work with GitHub Copilot or some type of AI coding assistant. We're working a lot with Foundry, Solidity. For you Windows users, we're assuming you're using Windows WSL or a Linux-like environment. You have a fundamental understanding of Solidity, a general understanding of what a byte is and what a bit is, and a basic understanding of the layout of storage. Now, if everything I just said there was gibberish, you can learn all of that and more on Cyfrin Updraft. There's a link in the description of this video, which will lead you to all of the code that we're going to be working with in this video and on Cyfrin Updraft. So please use that as a reference as the video goes on. But for those of you who really want to learn opcodes, inline assembly, YUL, or be able to look at an unverified smart contract on Etherscan and go, you know what, I could take the time and figure out what this is doing, this is the video for you. Break out your text editor and enjoy. All right, so here we are in our VS Code, our Opcodes FV. For this course, I do have GitHub Pilot installed and set to on for this. And I do highly recommend you coding along with an AI extension or an AI buddy. I promise you it's going to make you so much faster. If there is a VS Code extension that is AI friendly, that's not GitHub Copilot, I recommend that as well, because Microsoft is kind of dominating right now, and that's a little spooky to me. But beside the point. So let's go ahead. Let's open up our terminal. Let's create a new folder. So mkdir one horse store, or whatever you want to call it. Let's open that up like this. And I have an issue in VS Code for why that keeps coming up. Looks like Macs are having an issue as of recording. And now we're in a new folder here. We're going to do forge init. Of course, you know the drill. Set up our new Foundry project. And great, we have Foundry set up here. So let's pop over to the README, delete everything. And let's set out for our first task, which is going to be really easy. Write a basic, simple storage / horse store contract. And if you want, you can even go right to the GitHub associated with this. And you can just go to src, horse store v1, horse store.sol, and copy this. And you know what? I'm even just going to do that because it's really simple. Let's delete all these. Delete, goodbye. In src, we're going to make a new folder, horse store v1, and in here, new file, horse store.sol. I'm going to paste this in here. Now, additionally, if you're going through this code base, we also in the v1 section, we have this horse store symbolic.t.sol. For this section, we're actually not going to be doing this, but actually in the next section, we're going to come back to horse store to actually set up a real minimalistic symbolic execution or formal verification test. So if you see this in the code base and you're like, what the heck is that? Don't worry about this until the next section, the math masters section, where we're going to introduce you to formal verification. So if this is looking like gibberish to you, you need to go back and you need to finish the advanced foundry section or even the basic Solidity section. This should be very familiar to you. Like I said, we have a storage variable up here, number of horses. We have an update function, a way to update it, and we have a way to read it. So from a Solidity perspective, this is incredibly minimal code. However, if we pull up our terminal and we do forge build, this should work. We get successful. We can now come to the out folder, go into the horse store.json, and I'm actually going to pull up the command palette here with Command Shift P, or you can also do view command palette or whatever it is, or just Google how to pull up the command palette on VS Code. And I'm going to do format document just so that the JSON kind of forms nicely. And then I'm also going to pull up the command palette and do toggle word wrap, which makes it look horrible, but it'll help us a lot. So this is our horse store.json. So this is really the output of our compiler. This is all this stuff. Obviously, we have the ABI. I'm going to minimize that. And then we have the bytecode, which is really what we're going to be looking at, the deployed bytecode, method identifiers, and then some other stuff. There's a whole bunch of stuff in here, but whatever. This bytecode and this bytecode is what we're going to be looking at, both of these bytecodes. And they do something different. If you followed along in Cyfrin Updraft, we've kind of told you what the differences in these are, but we'll make it a little bit more clear in a minute. Now, in any smart contract, when it's created or when you send a transaction to it, you're always sending this call data or working with this call data. You're always sending raw bytes, raw data to the blockchain. And if you scroll down into the transaction, you can see we just view the original of this transaction. This is exactly what was sent to the blockchain. So when I send a transaction, we're going to have all this call data, right? And this data could be literally anything. We're assuming the smart contract that we send this call data to has a way to process or understand what this call data is supposed to do. And if we look at a contract and we scroll all the way to the bottom, we see all this hex, all this random data down here. It's this random data. It's all this hex that's responsible for processing that call data and governing what the smart contract actually does. It's all of this hex that makes up the different opcodes or the machine readable instructions. Every 1 byte or every 2 characters in this hex essentially makes up an opcode. There's some exceptions when you push raw values in the stack, but we'll talk about that later. We as human beings are terrible at understanding machine level code. We don't really know how 0 and 1s work. We don't know how to work with thousands of transistors at a time. We don't really know how to send instructions to transistors very easily. So when we write code, we write it in what's called higher level languages like Solidity that are more easy for human beings to understand. Machines, however, don't understand Solidity. They understand machine code. At the lowest level, the Ethereum virtual machine is exactly that. It's a machine. And so in order for it to do anything, it needs very specific instructions that tell it, hey, put this data in storage. Hey, put this data in memory. Hey, put this data in the stack. We'll learn about the stack later, etc. And it's all of these, and all of these machine readable instructions are also known as opcodes. So this Ethereum virtual machine that you've heard a lot about before, this magical thing that doesn't really exist, however, it's implemented. So the Ethereum virtual machine is this fake machine that says, okay, when you send data to the blockchain to Ethereum, convert that to, send money, send tokens or whatever. And all of those instructions of the Ethereum virtual machine are in these opcodes for the EVM. So whenever you say, for example, hey, store the number 7 at storage slot 0, there's a set of opcodes that are going to do that. There are a set of machine readable codes. It's all these opcodes combined that make up the EVM. Opcodes are machine readable codes, and it's the combination of all these opcodes that make up the EVM. So the EVM is really just this agreed upon set of opcodes that we say does stuff. It's a virtual machine because There's technically no like Ethereum machine. Whenever you run a node, your computer actually pretends to be this stack machine, this Ethereum virtual machine. Don't worry about that too much for now. Opcodes are these very specific machine level instructions. And you can see a list of them if you go to the ethereum.org website. Opcodes are pretty common in computer science. It's also known as instruction machine code, instruction syllable. There's a ton of different words for it. Opcodes in general are very common in computer science as a whole. However, in the smart contracts themselves, these need to be a set of these opcodes. These need to be a set of these machine readable instructions so that when we do send call data, when we do send data to these smart contracts, they have a way to actually interpret the call data and work with the call data. And if we scroll all the way down to the bottom, we can see the actual contract creation code. We can see deployed bytecode, etc. And all of these in the contract creation code and deployed bytecode is going to be opcodes. Typically, each 2 of these digits is going to be so this 60 at the start of this contract, we can actually copy this. And I'm going to go to one of my favorite sites for learning about opcodes, evm.codes. I can paste that 60 in and I can see what the 60 stands for. So the 60 opcode, which again is going to be the hex. So we could do cast to base OX6 dec, which is the 96th opcode, or we could see the binary. This is what the binary of that opcode looks like. So this 60 opcode stands for the push 1 opcode, which is going to place 1 byte item onto the stack. We'll learn what the stack is in a little bit, but there's going to be some familiar opcodes in here like mstore and sstore and sload and mload, right? We've learned about those in the Foundry Flow course when learning about some gas optimizations. So this contract is just this massive set of these opcodes, which essentially tell our machines exactly how to process this call data that gets sent to them. In the Ethereum world, we can actually change or add opcodes through the Ethereum improvement proposals. As of recording, a few months ago, they added the push 0 opcode, which was awesome. So just to recap, in a smart contract is going to be a set of opcodes combined, where in the contract code, every 2 of these hexes stands for 1 byte, and each opcode is 1 byte long, and we can see what each one of these opcodes does. Again, there are going to be some scenarios where it's not every 2, because, for example, we could do like push 4, where we place 4 bytes onto the stack. So we would see like a 63 and then 4 bytes instead of 2 opcodes back to back, right? So, but don't worry about that too much for now. Main thing is, boom, this is an opcode. 60 stands for push 1. 60 stands for push 1. Boom. 60, this is not an opcode. This is going to be how much is going to be pushed to the stack. This is an opcode. 52 is another opcode, which stands for mstore. So lots of opcodes. If this isn't making sense to you right now, it's okay. It will. Okay, now that we've learned about opcodes, we're actually going to go ahead and rewrite our horsestore.sol into Huff. Why are we learning Huff? Well, again, if you learn Huff, surprisingly, all of this EVM opcode stuff just becomes easier, because it really becomes easy to see how these smart contracts work at the lowest level. So let's go ahead and get started working with and installing Huff. In order for us to install Huff, we need to install the Huff documentation. If you're following along with the course GitHub, if we scroll down into our curriculum, we have a link to the Huff documentation right in the GitHub there. And this is the Huff documentation. You can go ahead and go to the getting started and follow along with the docs here in order to install Huff. I find the easiest way to install Huff is to first install this Huff up command. And all we need to do to install it is to run this command, which will download this sh bit and then run bash on it. So I'm going to go ahead and install Huff up by pasting this into your terminal. Great. And after this runs successfully, again, you'll probably need a Linux-like environment in order to do this. You'll get an output that looks something like detected your preferred shell as bash and added Huff to your path. And it'll add this to your bash RC. So you need to run this command first and then run Huff up to install the Huff compiler. Once Huff up is done, you should be able to do huffc -- version and get an output that looks like this. Now, depending on the shell that you're working with, you want to make sure that it actually was correctly added to your bash RC, your bash profile, or your ZCH, or whatever config file that your shell works with. So I want you to go ahead and actually delete your shell by hitting the little trash can or closing out of the terminal or whatever, pulling it back up, and then doing huff c -- version again. If you don't get an output here, but you got an output last time, that means that Huff wasn't correctly added to your bash RC or your bash profile or your ZCH or whatever terminal you're working with's config file. If you're running into issues here, this is a great time to chat with ChatGPT, Google around, figure out exactly what's going on here. If you're not using WSL, you can of course use the Windows installation or whatever installation process you want here. But remember, installing stuff is often the most frustrating part of development work. So don't get too frustrated if it doesn't work right away, and be sure to Google around and ask your AI buddies for help. Or of course, come to the GitHub discussions associated with this course. As we're coding along here, be sure to use the docs as a reference guide as well, because the docs are going to be the most up to date. The docs are incredibly helpful, and there's a whole ecosystem around the Huff code bases. But great, now that we have Huff C installed, we can actually start writing some Huff smart contracts. Let's actually rewrite our horse store in Huff, and rewriting it in Huff will actually teach us how smart contracts work at the lowest level, and will teach us a ton about these opcodes. To get started rewriting our smart contract in Huff, let's go ahead and create a new file. We'll call it horsestore.huff. And what's cool is what's cool about this is because we have these two smart contracts should be exactly the same. This one just written in a different language. When we actually go to write tests, we can write one suite of tests and just apply it to both contracts. This is also known as differential testing. And if done with fuzzing, it's sometimes called differential fuzzing. And it's incredibly powerful for people looking to build code bases in Solidity and then optimize them in a much faster, much more powerful, lower level language like Huff. You write your main smart contracts in Solidity so that they're easier to read, easier to understand, and then you either formally verify or you fuzz them against your gas optimized edition that you actually deployed to the blockchain. But anyways, let's get started working with Huff here. Now, when we work with a Solidity smart contract, let's say we deployed this contract on chain. If I call the function read number of horses, we almost kind of magically get it to return this number of horses. You know, for example, if I had deployed this smart contract, our horse store in Remix, right? I deployed it down here. I do read number. We almost kind of magically get the response 0 back when I call 1 to update the number of horses and rerun. Sorry, that was kind of zoomed out, but you get the picture. When I call read number of horses, I almost magically get this 1 to get returned to us. But when we actually make this call, when we actually make any call, if I actually call update number of horses again in Remix, and we could see this in Foundry too, you know that we actually send, the input that we sent is actually a whole bunch of binary itself, a whole bunch of just data itself. So if I copy this binary of the input of update horse, put a little comment here, paste it, it's actually this kind of ridiculous jumble of numbers. When we call update horse number and we add a value here, this data that gets input to the smart contract is called the call data. So this whole thing is the call data. And it's this call data that tells our smart contract, hey, this is what I want you to do. So how does Solidity know that this jumble of numbers tells the EVM, tells our smart contract, hey, update that number of horses? This jumble of letters. So we have two questions here. How did Remix know that when we press this update number of horses to send this exact data string to our smart contract? And then number two, how does Remix even know to update this storage variable with this jumble of binary bytes data? Like, how did this happen? So these are the two questions that we're going to answer now, and we're going to answer them by learning Huff. Let's start by answering this first question. Where did this data come from? Now, if you've taken the Foundry Advanced course, you know what a function selector is. You know we have this update horse number and a uint256. The two of these are the function signature, and we can hash them to make the function selector. So if I do cast sig update horse number uint256, I get this OXCDFEA2E or whatever it is, right? Let me actually copy paste this from Remix. So this, as we can see, actually matches the first part of this huge chunk of data that was sent in. So this is what's known as the function selector, right? So when we send this data to our smart contract, we're saying, hey, use the function that has the selector. So this CDFEA2E matches right here. So somehow Solidity knows, our smart contract knows, to take the first 4 bytes of the call data and use that to actually pick which function we're referring to. This is actually called function dispatching, and it's something that Solidity does natively for us. So there's no code in here that basically says, if the call data has 4 bytes that match the update horse number function selector, you should call it. It doesn't have that. It does that natively for us when it compiles. Now, instead of update horse number, we did casig read number of horses. This would be the function selector, right? And so when we send this call data to our smart contract goes, okay, I'm going to dispatch your function call to read number of horses because that's what your function selector tells me to do. So again, this happens on the back end for Solidity. Solidity sets up this function dispatching for us. But if we're going to write our smart contract in pure opcodes, which essentially is what Huff does, we actually have to write that function dispatcher ourselves. So this is already one of the most powerful things that we can learn right from working with Huff is function dispatching. So again, the flow will look like we send the call data, our smart contract reads our call data and goes, okay, what function selector are you looking for? You're looking for this function. I'm going to route your call to that function. In a way, us sending call data to a smart contract is going to be the same as us calling like a Python script or a JavaScript script. And we need an entry point for our call data to be processed. In Huff, we call that entry point main. In the binary, it'll just take your call data and execute it through whatever binary is there, but we'll talk about that in a bit. And again, I know I'm throwing a lot of terminology at you here, but I promise it'll make sense. Just follow along with me for now. We're going to really dial this in for you. So we need to actually code this function dispatching. So in order for us to have an entry point for our call data, we need to define a function that we're going to call main in Huff. Now, the Huff language does have functions, but for the most part, we're going to ignore functions exist in Huff, and we're just going to work with macros. For all intents and purposes, macros essentially are functions. They're a little bit different. Don't worry about the difference for now. So we're going to write a main function, which will do this function dispatching. And remember, we don't have to do this in Solidity, but we do have to do this in Huff. And importantly, we do have to do this in our bytecode as well. So learning how to do it in Huff will teach us how it's done in the bytecode. So let's get started. So we're going to define macro main like this. Now I am going to put the rest of the syntax for this, but don't worry about what it means quite yet. I'm going to say takes 0, returns 0. So this is how you define a macro, which is basically a function in Huff. Define macro, name of the macro, and then takes and returns. So the takes and returns refer to what it's going to take off the stack and return onto the stack, but don't worry about that yet. Boom, we have our main function. Oops, and sorry, the main macro needs to be uppercase, not lowercase. Now we can even test that this compiles by running huffc on it. So we'll do huffc, src, horse store v1, horse store.huff, and we'll get compiling and then no output, which means it compiled successfully. We can actually rerun the command and do -b, and we'll actually get the bytecode associated with just this smart contract. So just this smart contract, just this bit of Huff returns all of this bytecode here, all of these little opcodes. And we're going to come back to what those opcodes mean. But when we do the -b, we get the output of the binary here. Boom, we have a minimal Huff smart contract, which looks like this. And this is the smallest, most basic smart contract you can have, and we haven't done anything really. Now, additionally, I have some syntax highlighting in here. I'm using a Huff extension. So if you're using VS Code and you want to have some syntax highlighting for Huff, install this extension. It'll give you these nice little highlightings here. So we're still in the process of trying to make the function dispatcher, right? We're still in the process of us trying to code this bit that says, okay, if this is your function selector, call this function. But we saw actually when we compile this, we got this output here, but clearly we still haven't coded our function dispatcher. We just coded this main function. So what is this? What is this code doing? Well, when you compile any smart contract, most smart contracts are compiled into 3 or 4 different sections. The contract creation code, the runtime code, and then the metadata, and then sometimes constructors and whatever else the compiler feels like doing. The Solidity compiler does this nice little bit of opcode syntax where it adds a little invalid opcode between the different sections, so it's even easier to tell which section is which. So after contract creation, they pop a little invalid. After the runtime, they pop a little invalid. After the metadata, they don't pop anything because the contract's done. But these 3 sections are typically how a smart contract is created. The first section, or the contract creation part of the code, is what code that tells the blockchain to actually store the smart contract. This first chunk here, even if we have no what's called runtime code, this is still our contract creation bytecode. So when we finish this in Huff, we're actually gonna have 2 sections. We're gonna have the contract creation bytecode. We're gonna have this runtime code, and we're not gonna have any metadata, but we could add metadata if we want. Solidity and Viper natively add metadata to their smart contracts. We'll go through what this contract creation bytecode typically does, but this is a minimalist example of what the contract creation bytecode looks like. All this contract creation bytecode is responsible for doing is taking your smart contract and saving it on chain. Because in order for us to deploy any smart contract, here's an example of a transaction that created a smart contract. In order for us to deploy a smart contract, we send Ethereum some call data. We send it just a huge lump of binary. So in this giant lump of call data, in this giant lump of binary, the first section of this is going to be, yes, this contract creation bytecode. All this usually says is essentially, hey, take the binary after me and stick it on chain. That's essentially all the contract creation bytecode does. And we'll go through the opcodes and how this actually works. But essentially it says, hey, copy the next chunk of code, save it on chain, please and thank you. And that's essentially how the contract creation bytecode works. So even though we have no runtime code, we haven't coded anything, Huff is smart enough to know that we at least need a contract creation bytecode. And even if we compile this Huff smart contract that doesn't do anything, we have this contract creation bytecode here. You can actually typically tell that something is a contract creation bytecode by looking for the code copy opcode. So we talked about opcodes in the Foundry Flow course, but as we know, all these little 60, all these little numbers are referring to some type of opcode. And there's a phenomenal website that teaches us all these opcodes and actually gives us a little playground to try them out and teaches us what they do. But the opcode that actually says, hey, stick this smart contract on chain is going to be this opcode called code copy. So typically if you see this code copy opcode or the 39 opcode, that's an indication that you're looking at the contract creation part of the code base. Typically, you can still have this in the runtime, but if you're looking for a quick litmus test of what section of the code you're in, you can look for this 39. And if we look in here, we do indeed see, okay, so we see F3, 3D, 39. We do indeed see there's a code copy opcode in this contract creation bytecode. So again, we're going to go over what this does in a little bit. Make sense? Okay, let's continue. Now in Solidity, when we're working with variables, Solidity almost kind of magically just knows where to put them. They know magically if it's a memory variable or if it's a storage variable and what variables to kill after a program has ended. So number of horses here is clearly a storage variable. So after a program finishes, it'll keep that value to persist. However, some memory variable, like if I added uint256 hello equals 7, once the transaction to update horse number finishes, this hello variable will be inaccessible. It won't matter anymore. So how does Solidity know what to keep and what to get rid of, and how does it compute all this different stuff? And we have to ask this question in order to answer this question. So I kind of reformatted our questions here because we're getting more and more. And also, more importantly, how does the EVM know what to do with this? Does it just stick everything in storage for a little bit and then move it around? Unlike in Solidity will kind of magically say, okay, this call data, I know where to put it, I know what to do with it. But guess what? We are writing Huff code. We are essentially going to be doing the opcodes ourselves here. Now, in order for us to understand what places we can put stuff, we want to take a look at this tweet from a very prevalent smart contract developer in this space, Pascal. And I'll have this image in the GitHub associated with this course. He gave us this image of some of the most important places we can actually store data once transient storage comes into play. Transient storage isn't quite a thing quite yet. Don't worry about that for now. But these are some of the different things that the EVM actually can work with and keep track of. The most important ones that we're going to be looking at are going to be the stack, memory, and storage. There's also obviously the EVM code itself. We have a program counter and available gas. Transient storage doesn't quite exist yet and is not super important for what we're going to be covering here. But we are going to focus on the stack, memory, and account storage. So when we're looking to grab this data and work with this data, if we want to do any type of computations, we first need to figure out where do we want to do computations? Where do we want to put this data? So the EVM is what's known as a stack machine. Out of all these places, the cheapest places gas-wise to do stuff is going to be on the stack. And we actually know this because if we go back to this evm.codes website, we have this minimum gas, which gives us a clue as to how much gas each one of these operations are going to do. This add operation, what it does is it takes the first two items on the stack and returns onto this stack data structure the addition of the two of them, and it costs around 3 gas. And if you look for another add opcode, you'll see that the only way to add two things in the EVM world is on the stack. So at some point or another, if you want to add anything, it needs to be on the stack. EVM is known as a stack machine or stack state machine, where most of the operations we're going to be working with are going to be putting stuff on and pulling stuff off of what's called a stack. Now, the stack is going to be the main data structure that we work with when it comes to working with Ethereum. And you can think of it literally as a stack, like a stack of pancakes or a stack of books. Whenever we have an object on the stack, if we push something to the stack, that's when we basically drop it from the top and stick it to the top of the stack. If we want to add a new item to the stack, well, guess what? Same thing. We got to bring it to the top and drop it onto the top of the stack. Now we have an item on the bottom of the stack and an item on top of this object on the stack. If we wanted to get the value in here, let's say this was some 7, let's say this was 100. If we wanted to get to this 7, we would need to first pull off the 100 and then pull off the 7. This is how the EVM works. And this is how we're going to do most operations. So whenever we see any of these opcodes that we're going to be learning about, we can kind of visually represent what they're doing with an object that looks like this. So most of what we're going to be doing is on the stack. Now, the other two important places that we can put and do stuff is going to be memory and storage. Now, unlike the stack where you have to pull things on and off one at a time, memory, you can really stick any variable any place that you want. And at the end of your transaction, poof, everything in there goes away. Storage kind of works the same. You can think of it as a giant array where we can stick data wherever we want, whenever we want. And when the transaction completes, storage persists. However, as we know, as we've learned before, anytime we interact with storage, it's going to be incredibly expensive. If we go to our opcodes, the store opcode, which saves a word to storage, costs substantially more than our mstore opcode, which saves a word to memory. mstore, minimum of 3, store, minimum of 100. So storage is always going to be a lot more expensive. But these are going to be the main places we can work with data. You can think of memory like a giant array. You think of storage like a giant array that persists after the transaction completes. And the stack is literally a stack of pancakes. And the stack is where we're going to do most of our computation and most of our operations. So anytime you want to add stuff, you want to subtract stuff, you want to do anything, you have to do it in the stack. There's sometimes we have to do some stuff in memory, and we'll point those out when we get to them. Now, like we said, there are a couple other places you can actually store data and work with stuff, but for the most part, just think stack, memory, or storage. That's where stuff is. That's where data is going to go. And all of these opcodes, all they essentially do is do stuff to the stack, memory, and storage. That's basically it, with the stack being the most important piece. In fact, right at the top of all these opcodes, you can see this little stack input and stack output. Most opcodes say, okay, A is going to be the top of the stack, B is right underneath the stack, and what the add opcode is going to do, it's going to take the A opcode plus the B opcode and then return on top of the stack A plus B. So if we have a stack here and we want to use the add opcode, we would need to have two stuff on the stack. Well, in order to get stuff on the stack, we actually need to use a push opcode. And there's a whole bunch of push opcodes here. The push opcode has a push and then the number of bytes you want to place on the stack, except for push 0, which always pushes 0 onto the stack. So let's say we called push 1 with a value of 0x01. What we would do is we would push 1 onto the stack, and now this is on our stack with a value of 1. Remember, we're always going to be working with hex data, so 0x01 is going to equal 1. Now, let's say we called push again with push 1, so we're going to push 1 bytecode on, and then instead we do 0x03, which is going to equal 3. So now we have 3 on top of the stack and 1 right underneath it. If we came along and said, okay, we want to now do the add opcode, what's going to happen is our add opcode is going to look at the top of the stack and right underneath the stack and say, okay, we're going to add 3 plus 1, and the resulting value on the stack is going to be what the addition of them is. So you can almost think of them being pulled off. Our little add code going, okay, 3 plus 1 is 4. So we're going to do 4 here, 4, boop, and now stick that on the stack. If this is what our stack looked like, if we had 4, maybe 3 at the bottom, maybe 1 here, and we called the add opcode, remember, it only applies to the 2 top on the stack. So essentially it would say, okay, let's take these. 1 plus 4 is 5. So now the data here is going to be 5. Let's stick that back on the stack. And after an add opcode works, this is what it will look like. So that's an example of working with 2 really important opcodes, the push opcode and the add opcode. Push is going to stick stuff into the stack. Add is going to take stuff off the stack and combine them. And you can read all the different inputs and stack outputs in EVM.codes. They do a great job of that as well. And we'll see in a little bit how opcodes like mstore and store take stuff off the stack, but then stick stuff into memory as a result of what's on the stack. So we'll see that in a bit. How do we make this contract dispatch our call data so that when we send it call data, telling it to update our horse numbers, it actually updates our horse numbers? Okay, let's continue doing that now. So we now know when somebody is going to call our horse store smart contract, they're going to call with something that might look like this, right? They're going to send it this giant lump of data. Let's find the function selector so that we can route it to the code that actually updates the number of horses, which we haven't written yet, but we will. Now that we know that the EVM is a stack machine, and in order for us to do this function selector routing, we need to do some computation on the stack. Let's try to actually get this to work now. Now, just for this beginning part, I'm going to do 2 things. I'm going to have our little stack over here, and I'm going to push stuff onto the stack to make it a little bit more obvious what's actually going on. But the second bit here is we are going to do a little bit of magic just in the beginning of this main function to do this function dispatching, because there are a couple of opcodes that are going to be a little confusing the first time you look at them. Once again, stick with me. I promise this will make sense as we go back over it. So the first thing that we want to do is we actually want to push 0 onto the stack to do some stuff later. So typically to do that, you would have the push 0 opcode, which would literally just push 0 onto the stack. Boop, like this. In Huff, Huff is actually smart enough to know that if you just do 0x00 like this, it's smart enough to say, oh, okay, this is the push 0 opcode, and they want to push 0 on the stack. And similarly, if I wanted to do like push 1, 0x01, if I wanted to push 1 byte onto the stack with the value 0x01, I wouldn't even need to have the push 1 opcode in Huff. Huff is smart enough to know that if I put 0x01, they know that I mean push 1, 0x01, because obviously this is 1 byte long. If I did this, it would be smart enough to make that push 2, because this is, of course, 2 bytes long. So when doing push opcodes in Huff, you just need to put the actual value that you want to push onto the stack. So in our Huff now, when somebody calls this smart contract, and when somebody sends any call data to this smart contract, the only thing this smart contract will do right now is push 0 onto the stack. That's it. And in fact, we can even compile this with huffc, src, horsestore v1, horsestore.huff. Oh, and let's add the binary. And we can see our code is a little longer than just the contract creation bytecode now. Now, after the F3, after that contract creation code, we now have this 5F, which if we go back to evm.codes, 5F is, indeed, it's the push 0 opcode. So we can see just by adding this push 0 opcode in our Huff, we've added the 5F opcode, and now there's a 5F added into our smart contract. This means that, once again, since this is our main function, and since it's the first, anytime anybody says any data to the smart contract, we just push 0 onto the stack. That's it. So this doesn't do anything yet except for push 0 on the stack. But cool. So we're already starting to code with pure opcodes. Very exciting. Okay, what next? Okay, well, somebody's going to send us some call data, right? And they're going to have the function selector embedded in the call data. So we want to actually get their call data. And to get this first chunk, we're going to need to do some operations, right? We're going to need to say, hey, give me the call data, but like only the first 4 bytes. So to do any type of operations, what do? You guessed it, we got to stick it on the stack. And I want you to keep that in mind. Anytime you want to do any operations, you got to stick it on the stack. So if we go back to our evm.codes, we can look for call data load. And this is the opcode that actually loads our call data onto the stack. So you can even read it in evm.codes. So what it's going to do is it's going to take a stack input and give a stack output. And the stack input of call data load is why we actually pushed the 0 onto the stack in the first place. So what call data load is going to do is it's going to look at the call data and it's going to grab whatever value is at the top of the stack and use this as the bytes offset. So if this was 1, if we pushed 1 onto here, what our call data load would do is it would look at our call data and go, okay, I'm going to load this call data, but I'm going to ignore the first byte and start from here. We don't want it to ignore the first byte because that first byte includes part of the function selector. So as of now, here's what our stack looks like. And usually when I'm coding, I like to visualize the stack in comments as well. So if I have 0x0, 0x0, which pushes 0 onto the stack, I also like to do these comments where I have like a little brackets and like a 0 in here, which says, okay, at the bottom of our stack is 0. So this little comment here and this image are supposed to represent the same thing. If I were to add like 0x02, I would then do something like this, where I would say 2, 0, where the left side is going to be the top of the stack and the right side is going to be the bottom of the stack. As a stack image over here, that would look like this. So I'm going to keep this commented out for now, but as I'm coding along, this is how in the comments in your code, you can also keep track of what the stack looks like. So I'm going to delete that for now. So since we have 0 on the stack right now, when we do the call data load opcode, and this is how you do it in Huff, you literally just write the name of it. It's just going to put the call data right onto the stack, starting from the 0th byte. So it's going to add the entire call data right onto the stack. And you might be confused. You might be saying, hey, we replaced the 0 with the call data. Like, why did we do that? Well, what happened was we had this call data. We have this call data that's being sent to our smart contract, and we called the call data opcode. And what it did was it says, okay, let's pop off this 0 and let's stick this call data on starting from the 0th. Since if you start from the 0th byte, that's just all the call data. We just said, okay, we've popped off the 0, and now all that's on the stack is the call data, is this big thing right here. So cool. Now we have the whole call data onto our stack here. Great. What's next? Next is the hard part. And if you don't understand this part, that's totally okay. Because what we need to do is we need to lop off all of this, right? Because just this is our function selector. So how do we cut down the call data to just the function selector? We have this huge thing, and we only want this. So how do we cut it down? There must be an opcode that will help us do this pretty easily. So there's a lot of approaches we can take to do this, but one of the easiest and most efficient ones is going to be this SHR. This is where we're going to shift the bits towards the least significant one. And to do this, you need 2 values on the stack. You need a shift number of bits to shift to the right, and the value, the 32 bytes that you want to shift. So this SHR is the right shift for bits. But for the SHR opcode, let's say this is our text. This is our hex here. 0x01, 021. So this is in bytes, of course, right? Each 2 of these, oh, excuse me, let's get rid of that one. This is a byte, and this is a byte. And as we know, 1 byte equals 8 bits. So the shift opcode is how many bits to shift to the right. So if we look at this as being 2 sets of 8 bits, we can actually rewrite this. We can use cast if we want. We do cast --2 base, grab this and say bin for binary, and boom, this is it in bits or in its binary. We go 1, 2, 3, 4, 5, 6, 7, 8. This first part represents the 02, and this 1 over here represents the 01, right? If I change this to like an F1, we're going to see we're going to get a much different value, 0xF102, with, it's going to be a lot bigger, obviously, because that F1 is now going to use all 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8, boom. This is the 02, and this is going to be the F1. Okay, hopefully you're following along with me. If you're not following along with me, play with this cast to base between bin, dec, and hex. So this is the hex, this is the bin, and then what was dec? Dec, 6,100, whatever, right? That's the decimal equivalent of that binary. Anyways, so this is the binary representation of this hex. So if we say this is the value that we want to shift, and we want to shift it by 2, well, what are we going to get? Well, we're going to shift off these 2 values here and shift everything else to the right. So now this is going to be our value. 1, 2, 3, 4, 5, 6, 7, 8. This is going to be what's left. And we can pull up cast and see what this is in both hex and in decimals. And we'll put a 0b at the front of this to tell cast this is a binary. But if we take this and we do cast, you can actually do --2 base, or you can actually just do 2 base, paste this in with the 0b to tell Foundry it's a binary. And we say hex, we get resulted with 0x40, which again, if we do the decimal, we get 64. So if we shift over 2 bits, this is 0, 012, excuse me. If we shift over 2 bits, we get 040. Let's shift over 2 more bits, right? So let's do 4 bits, right? So that would be 2 more. Copy this, do the same thing, paste it in. Decimal is going to be 16. The hex is going to be 0x10. So what this right shift does is it just pushes the whole thing to the right a number of bits until we're left with whatever is left over. We can actually validate if we did this correct in our heads, right? So we had this 0x012. Let's say we have this 0x012. We want to push it by 4. We said we got what? We got 16. We can actually see that this is correct by trying this out right in our even.codes.playground. So there's this playground tab here where you can actually switch to playing with Yule, Solidity, bytecodes, and then opcodes as well. So we're going to go to mnemonic because that's going to be opcodes. SHR needs a value and then a shift. So shift needs to be the top of the stack. So first thing we need to do is we need to push to this onto our stack, right? So we're going to push this onto our stack so that this is now it's on the stack. Then we need to push 1, 4. So we're going to push this onto the stack. We're going to push 4 onto the stack, and then we're going to do a right shift. So when we do this playground here, what's going to happen is we're going to push 0x0102 onto the stack. Then we're going to push 0x04 onto the stack. Then we're going to call SHR, which is going to shift this to the right by 4. And what we're going to be left with is poof, this value shifted to the right by 4. So let's see what this looks like when we actually run this in our playground here. If we click run, and we zoom out just a hair, we have our opcodes up here. And down here, we'll have our stack, storage, etc. It's like there's not really a way for me to keep both in frame at the same time, but I guess we'll have to make do here. So if I want to step into this, we can go opcode by opcode. So first, let's do the push to 0102. Boom, step into it. After that executes, we scroll down here, we now see 102 is now on the stack. So now we're going to push, oops, excuse me, this should be push 0x04. Sorry, let's run that again. 0102, great. Now we're going to push 1, 0x04. Okay, let's run that. Okay, great. Now our stack has 0x04 at the top and 0x0102 at the bottom of the stack. Based off our calculations here, we should return 16. So now let's go ahead and step into it. We get 10 on the stack, and this is the hex here. So if we do cast to base 0x10 decimal, we see we do indeed get 16. So our math here is right, and we've learned how a right shift with all of our bits works. Now, when we do this call data load opcode, the call data load can only put 32 bytes onto the stack. So if this is our call data, again, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 60, 1, 2, 3, 4, 64 of these little numbers divided by 2, since every 2 numbers is a byte, is going to be 32. So this is 32 bytes. And when we call our call data load, it actually puts this onto the stack, not the entire call data. So these last couple of bytes are actually truncated. If we wanted to include these when we actually call the call data, we would increase the offset, right? We would increase the offset so that we could get this. But so when we call data, we only do 32 bytes on the stack. And the reason we're going to do this right shift is because we only want this. We don't want any of this. So what we can do is we can say, hey, let's right shift this whole thing, push it all the way to the right so that this is all that's left. Let's do that now that we learned how the right shift works. Anyways, back over here, we've just put our call data onto the stack. So now our call data is on the stack. Our call data looks like this. We want to shift this so that we only get the function selector so we can finally start doing our dispatch. So what we want to do is, again, back in our right shift opcode, we want to get on the stack the value we want to shift and the amount we want to actually shift it. So we have at the bottom of our stack the value we want to shift, right? We want to shift our call data all the way to the right. So how much do we want to shift it? This is going to be the first 32 bytes of call data is going to be on the stack, right? So this is the call data, or at least the 32 bytes. And remember, since it's only the first 32 bytes, we don't need to worry about this over here. So we're going to need to cut this down to just this. We're going to need to shift all of this to the right. So let's do a little bit of counting again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 40. 1, 2, 3, 4, 5, 6, 7, 8, 9, 50. 1, 2, 3, 4, 5, 6. So 56. So we need to right shift 56. So let's do a little calculating here. 56 divided by 2. So that's 28 bytes. 28 bytes. Or 28 times 8, since 1 byte is 8 bits, or 224 bits. So now there's a lot there, but that's what we need to do next. We need to do a right shift of 224 bits. So let's pull this up. Let's do cast to base 224 hex. That's 0xe0. So we need to do a push 1, 0xe0, but since Huff is smart enough to know that it's just 0xe0, boom, we can just do this. And now on our stack, on top of the call data, we have 0xe0. Now that these two are on our stack, holy moly, we're finally about to do it. We have the number we want to shift on the top, right? 0xe0, we want to shift by that many bits. We have the thing that we want to actually shift. We can actually now do the SHR opcode to actually do this shift. So if I grab this, if we want to even, boom, 0xe0, this is what it looks like now. Now we can run the SHR, which what this opcode is going to do is it's going to take this off, and go, okay, you want to shift this to the right by this much. Great, let's go ahead and do that. And we'll return onto the stack just what's ever left, which is going to be our function selector. So we're going to shift by this many bits, and all that's going to be left on the stack is that. So now we can even just say function selector. And I know this seems like a lot, but really, right, this is just a few opcodes. It's 0x00, call data load, 0xe0, and then a right shift. And just by doing that, we now get the function selector. So now we have the function selector on the stack. And once you have a function selector on the stack, you can now start to finally do some function dispatching. So great job. I know we've gone over a ton already here. So let's do a little bit of a recap of what we learned so far. So first off, we learned a little bit more about the EVM. We learned that there's a lot of different places to store and manipulate data. We have a stack, which is going to be the main data structure we're going to be working with. We've got memory, we've got storage, we've got gas all over the place. We even mentioned there was a program counter, gas available, and some other stuff. We learned that the stack is going to be the main data structure we're going to work with to manipulate data, where we can push data onto the stack, we can pop data off the stack, but we're always working with the top of the stack. The EVM is built into this list of opcodes, which essentially manipulates the stack and also memory and storage, etc. We learned that when we're working with these opcodes, most of the time we're going to be doing stuff to manipulate data on the stack and store it into memory and store it into storage for one reason or another. In our Solidity smart contracts, whenever we send data to a smart contract, we actually send this thing called call data. Solidity, intelligently enough, when it compiles into opcodes that can understand call data. When it gets call data, one of the first things it has to do is look at this call data and say, what would you like to do? And get this function selector. Once you get the function selector, you can actually route the rest of the call to the function associated with the function selector. We did this ourselves in raw opcodes in essentially Huff by first pushing 0 onto the stack, the call data, 0xe0, and then doing a right shift. And then what that left us with was the function selector. essentially we took this call data, lopped off the end here with our right shift, and all we were left with was, boom, this function selector. Now that we have the function selector, we can use this to say, okay, it's time to route your call to the correct function. We don't have any of the functions defined yet, so obviously we're going to need to do that as well. Now, if we do a little Huff C, src, horse store.huff, -b, you should get this to compile and get an output like this. And for now, if you want to play with Huff, you can come to the EVM.codes playground. Let's go to the playground here. Let me expand this. You can either do bytecode, where you can literally stick the bytecode in here. You can do mnemonic, where you can do opcodes, but this is a great place to play around with tinkering with opcodes. Foundry has a debug function as well that we're going to play with in a bit, but this is a great place to play with stuff. If you do copy paste the bytecode in here, just remember, half of this is going to be the contract creation code. So if we look for this 39 opcode, that we know that that's the code copy. This 3D, I already know is actually return F3, excuse me, F3 is going to be return. So I actually know that the runtime code starts here. And if I wanted to play with this, I could actually just put the runtime code that I created, and we can actually see it does match what we coded. Push 0, call data, push 1, E0, add. Oh, where'd the add come from? Oops, I forgot the C. Oh, okay. Whoops. Oh, forgot the C. Yep. Okay. Right shift. Perfect. And we can see if we were to send this, our call data, we're to copy all of this, stick it into here, get rid of those spaces. Now we hit run. We can now walk through this line by line, and we would see at the end on the stack would just be the function selector. So this is a great place to learn, to tinker, and play around with working and learning about opcodes. All right, so let's keep going. Right now, we have the function selector on the stack. Huzzah! Now we want to route this call to the correct function. In Solidity, when we call update horse numbers, it almost magically just knows what to do. When we're coding in bytecodes, we actually need to tell it that is actually calling to update the numbers or read horse numbers. So we're going to take this function selector and we're going to do a couple of comparisons. We're going to say, okay, now that we have this function selector, we want to jump to the function data associated with the selector. And in this contract, in this Huff, in this horse store, we've got two function selectors, update horse number and read number of horses. So we're basically going to say if the function selector equals update horse number, then jump to that code, which we haven't defined yet. And then if the F selector equals read the horse number, jump to that code. So let's go ahead and do that. I'm going to get rid of the stack image for a bit, but I'll bring it back when I think it's necessary. So let's do these comparisons. So we have these two function selectors, update horse number and read number of horses. So let's actually compute these with cast, right? So we can do cast, sig, little parenthesis, little quote, update horse number, UN256, like this. So this is going to be the function selector for update horse number. So this equals update. And then let's do the read as well. Cast, sig, paste, oops. Little quotes here. Read number of horses. It's going to be this one. So this equals read. So now that we have those, we're going to use these to basically check to see if the function selector matches one of these. We have an opcode that can actually check for matches in EVM.codes. In EVM.codes, or in our opcodes. In our opcodes, there's one called EQ, which stands for basically equals. And what it's going to do, it's going to look at the top of the stack. It's going to say the left side integer and the right side integer, and it's going to return A equals B, where it's going to return a 1 if the left side is equal to the right side, and then 0 otherwise. So if they match, it's going to be a 1. If they don't match, it's going to be a 0. So what we can do now that we have this function selector on the stack already is we can push this, which is our update, horse number selector, onto the stack. And now on the stack is not just going to be the function selector, but it's going to be the update horse number function selector, and then the function selector. And then we could do the equals. And this will be true if func selector matches. Boom, because it takes 2 inputs and returns 1 on the stack. So on the stack, there's these 2 inputs and it returns true if they are the same. Now that we have whether or not it's true, we want to add a little jump opcode. We're going to say jump to update horse number code if true. And to do this, we actually have 2 opcodes that we can work with. We have a jump and we have a jump if. So the jump opcode just jumps to some other spot in the code. The jump I, which stands for jump if, will jump to some other spot in the code if some condition is met. So the stack input is going to be the counter or the byte offset in the deployed code where execution will continue from, and then B, which is going to be our true or false. So basically, if B is true or anything other than 0, jump to this new program counter. So the program counter is not something we've spoken about, but the program counter is going to be the byte offset in the deployed code. The program counter can be a little bit confusing and a little bit tricky, so we're not going to go over it too deep for now. And because Huff gives us some syntax to make it a little bit easier, but once we compile this, I'll show you what I mean and it'll make a little bit more sense. So we want to use this jump I, this jump if opcode to actually jump to the update code base, which again, we haven't defined yet. So the way that we're going to do that in Huff here is we're going to add the program counter to jump to, right? Because the jump if opcode requires the program counter at the top of the stack and then the true false conditional. So we have the true false conditional. So we could either just do like manually add the program counter here, but Huff has some nice syntax. We can actually put some text here, which will define the program counter for a certain macro. So I'm going to do update jump. I'm going to just say update jump here. And what this is going to do now is on the stack, this update jump is going to have the update horse number program counter. And then of course the true false conditional. Before I finish doing this, I'm going to put down here this update jump and this colon, and then this set number of horses. I'm going to explain all this in a second. And then down here, I'll do a little define macro set number of horses equals takes 0, return 0, just like this. Now I just wrote a whole bunch of code, but let me explain it. So we put this update jump here, and what this update jump is since we have this conditional down here, we're basically saying, hey, this update jump keyword is going to refer to the program counter for set number of horses. This syntax here is a little bit of Huff sugar. Update jump refers to the program counter for set number of horses, wherever that ends up getting compiled to be. And right now our set number of horses macro does nothing because we haven't done anything with it yet. But basically now we'll say jump if or jump I, which again is going to take our program number and true false. And so if this is true, if this is anything other than 0, we're going to jump here. Otherwise, we're not going to do anything. So once this jump if happens, we've got nothing left on the stack. And we can even run this again. We'll compile this. C, oops, what did I do? Macro diff set number of horsey, set number of horses. Let's do it now, and boom, and this is our output. Now, if we want to practice, if we want to run this over in the EVM.codes playground, what we can actually do is we can make it even easier. We can do the Huff compiler and do --bin runtime, and this will give us just the runtime code, which is great. So now if I paste this in here, we can actually see pretty much exactly what we just coded in Huff in pure opcodes. We have push, call data, push, right shift, right? This is getting the function selector. Then we have push, which is checking the update function selector. We have an equals. We push that that program counter, and then we have a jump if, and then importantly, we have a jump dest. So this is something we didn't talk about quite yet. So when you do these jump opcodes, they can only jump to a jump dest opcode in the code. So if it's not jump dest, you can't jump there. So the jump dest is an opcode which literally just says, hey, this is a valid destination for jump or jump if. When we set this up, this update jump syntactical sugar, we're setting up, hey, set number of horses is now a valid jump destination. So we could have 100% manually done this instead of using the Huff syntactic sugar, right? So what we could have done was we could have said, okay, 0x000f jump if, and then had a jump dest down here, where if this jump dest was at program counter 0xf, this would be a valid jump destination. So, but it's a little confusing to do that when writing in Huff. So this syntactic sugar just makes it a little bit easier, just saying, hey, set this up as a jump destination. Update jump is going to be a valid jump destination, and and the code that's going to start there is going to be whatever code is in the macro set number of horses. So hopefully that makes sense. This is what it looks like when we actually compile it. Obviously, nothing's going to happen after the jump dest because we jump here, boom, nothing happens. So let's actually run this in our playground. With some valid call data in hex here. So if we want some valid call data in hex, we would need to have this at the beginning of our call data, boom, and then we could put, literally almost whatever else we wanted after it. We'll do run, and if we walk through this, we should be able to jump because on the stack is F and true, and boom, we should hit the jump dest. Now, if we don't have the correct function selector, right, this equal will return false. So I just got rid of it in the call data. I'm going to go ahead, run now, step. Once we get to this jump if, we have F and 0. So we have the jump destination, but we have false here instead of true. Now, if we enter we don't jump. However, we still go to the jump dest because that's next in line, right? So we basically just didn't jump and we went to next in line. I guess it's kind of confusing because no matter what, if we jump or we don't jump, the next opcode is the jump dest. So I guess that's not a great example there. But in any case, good job. We have now successfully done a function dispatch for the update number of horses. Good job. But what if they aren't calling the update horse number? What if instead they're calling the read, what is it? The read number of horses. Read number of horses with this function selector. Okay, well, that's easy. We just don't jump, right? No worries. Oh, but our stack has nothing on it, right? Up here, if we don't jump, we now continue with our stack with nothing on it. Oh, well, that's kind of annoying. Well, no worries. We could just run this again and get the function selector again so we could check to this one. We could 100% do that. But what's a lot easier and costs less gas is if once we get the function selector like this, before we do any checking, we actually duplicate it so that there's always a function selector on the stack. It costs less gas than doing all of these. It's one less opcode. And this is where a lot of the optimizations from coding in Huff versus Solidity sort of start to take shape. Solidity might not be as clever as you at doing some of these optimizations. Solidity, maybe it just goes, oh, okay, well, I'm just going to re-get the function selector the way that I got it before. Whereas it might be a lot smarter if instead we just duplicated the function selector. So I'm going to add an opcode here. We're going to add the dupe1 opcode. Oops, we'll go to evm.codes. Let's see what dupe1 does. It just duplicates the first item on the stack. The input, the top of the stack, is going to be the value to duplicate. And then it sticks on top of that the duplicated value. So now if I go back and I add this dupe1 opcode, all of my comments now need to get updated, right? So if we add dupe1 here, thank you ChatGPT, we're now going to have function selector. And when we add this, the update function selector comparison, the stack is now going to look like boom, function selector. When we do equals, the function selector is going to be underneath that. When we do the update jump, the function selector is going to be underneath that. And then when we do the jump if, the function selector is still going to be on the stack. So now if we don't jump, we still have the function selector, and we can just redo this process. So typically you'll see this setup for checking for function selectors in Huff and actually in Solidity. They'll duplicate the function selector, check to see if it matches another function selector, jump, and then do the same thing all over again. So we probably would, if we had more function selectors, do dupe one again. But since this is the last one, we can leave it off. So here we are. So now we want to do the same thing, but for read number of horses. We can skip the dupe one because this is our last function selector, right? So we have the original call data function selector on the stack. So what we want to do is we want to push the read call data function selector on the stack. And now we have the read function selector and then the call data function selector. And we can do the same thing. Let's compare if they're the same. So we have now just true if the function selector matches. We can now create a different jump destination. We'll call it read jump. And now on our stack, we're going to have the read jump, and we're going to have that true false conditional. I should probably do this to make it make more sense. And then after that read jump, we're going to do again a jump if. And if this is true, we're going to jump to the read jump, which we want to go ahead and make a read jump destination. We'll call this one, actually, yeah, thanks ChatGPT, get number of horses. Down here, define macro, get number of horses equals takes 0, returns 0, like that. And the function selector isn't on here anymore, and that's fine because we only had 2 we wanted to compare to anyways. So already, by learning Huff, you've learned how to make a more efficient function dispatcher than Solidity, because Solidity will have an extra dupe opcode here, extra dupe 1 opcode, which is going to cost gas. So congratulations, you've just leveled up just by doing this so far. So if we compile this, we should have 2 different jump destinations, one for updating the numbers and one for reading the numbers. So let's go ahead, let's compile this. Again, I'm going to do the bin time or the bin runtime. So this is just the runtime. Let me copy this and we'll paste this once again to the playground so we can really feel what's going on. And wow, look at that. So now we have 1 jump dest, we have 2 jump dests and 2 jump ifs. So it looks like the first one we're comparing for the update, and then we're comparing for the read. So let's go ahead, let's run through this. And again, we're going to be looking at the stack at the bottom. And let's see if once we hit here, it should jump down to here, right? If we pass in the correct function selector. So I'm actually going to copy it so that it should be the correct function selector. And we're going to go ahead and run this. So we do push 0, great. Jump to, yep. Cool, and now we're at this jump if, and here's what the stack looks like. We have a 1A, which is going to be what? This is going to be the program counter or the jump destination. We have a 1, which stands for true, and then we have the original function selector on our stack once we get to this opcode. Since this is true, our jump if should jump down to 1A, this valid jump dest, when I hit this step into button. And that's indeed what we see. Perfect. So our code is working the way we want it to work. We're getting valid jump destinations. Our code is compiling. Oh, this is so exciting. We're learning exactly how opcodes work and exactly how Solidity compiles our smart contracts into opcodes. And we're learning even more efficient ways to do it. So I know this is really low level. A lot of this can be confusing. So be sure to stop, pause, ask questions, etc., and tinker with some of these, right? Compile some different contracts, stick it into here, try to play with them, put in different call data values, etc., and see what happens. What will happen if we don't jump? What will happen if we don't jump anywhere? Well, the code will just keep going, right? The code will just keep going, and maybe it'll call whatever the next opcode is. In our case, the next opcode is these 2 jump dests, which cost gas, right? If we don't get a valid jump destination, we want our function dispatcher to end. We want it to revert. So what's good practice is to add some type of revert statement at the end here so that the code just doesn't continue to execute. And maybe even worse, it executes something you don't want it to execute. So if we do not get a valid function selector in the call data, we want this call to revert. And to do that, we're going to use the revert opcode. So if we go to evm.codes, we look up revert. Here's the revert opcode. It takes two things on the stack, which are going to be the offset and the size. So the offset is going to be the bytes offset in memory in bytes, and the return data of the calling context, and the size is going to be the size of memory to copy. If you wanted to revert with an error code, putting something into memory is how you would actually return with an error code. And this is how you would pick where in memory to actually return the data associated with the error code. For us, we're not going to do an error code. So we're going to say, great, just stick 0 and 0 on the stack and then revert. So on the stack, we would have put 0, 0. And then once we revert, there's nothing else on the stack. And same thing, if we compile this, and now we grab this, we go to our playground, paste it in here. If we run this without a valid function selector, so let's just do like 1, 1, 1, 1, 1, 1, 1 or something like that. What should happen is we shouldn't hit these jump desks, right? Because we should hit this revert before we jump here, before we jump to these. If this equals return true, we would jump to this jump desk. We would jump over the revert. But if we don't have a valid jump destination, we're going to run to this revert, which is what we want. So let's practice. We're going to put some dummy data in here. I hit run, step, 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 and then, oh, yep, sure enough, we landed on the revert. If I hit step again, boom, it's done, right? It doesn't go to these jump desks because the call reverts. And even in the little log here, we see revert. And we reverted with no data. So these jump desks don't get executed, and that's what we want. Great job. So we now have a function dispatcher. This is exactly what Solidity does and Viper does and all of our smart contracts do whenever they get a transaction, whenever they get call data. This is the first thing that they do. And later on in this section, when we break down the Solidity bytecode, you'll see that Solidity does this exact same thing, but with a few more opcodes, and you'll see why. Now we're going to do two things to make this a little bit nicer. I've kind of got a lot of comments in here that are making this a little bit difficult to read right now. And this function really isn't that many lines of code, but it looks like it's a ton of lines of code because of how many comments are in here. So I'm going to go ahead and delete most of my comments, but you put the amount of comments in your code base that you want. I'm also going to line up a lot of these jumps as well, a lot of these lines as well, because same reason, I want to make them a little bit easier to read. But yeah, you can do whatever you like to do. This, that, this, beautiful. Cool. See, this is actually what our main function dispatcher looks like, and that's a lot smaller than what it was before. So this one's going to be update number of horses. Bit of syntactic sugar that comes with Huff is actually making these function signatures, these function selectors, a little bit easier to read. What Huff has is this keyword called _, all caps, func_sig. And this will actually calculate the function signature for you, so you don't have to manually do it with cast or every single function selector that you're using. What you can do is at the top of your code, you can actually define a little interface. And in this interface, you can write the different functions as how they would be defined in Solidity, and Huff will take those and convert those into function selectors. So we'll do define function update horse number with a uint256, which is going to be non-payable, like so. So we have to do this non-payable bit in Huff. And then we'll also do define function read number of horses. And since this is a view function, we don't need non-payable, but this will return a uint256. And now that we have this Solidity-esque interface here, we can actually use these with this func_sig keyword. So now instead of adding the function selector directly here, what we just do is we do $func_sig, and then in here, we put update number of horses. So this will take the update number of horses function from our interface and convert it right for us in here. And we can do the same thing for read number of horses. Copy that, paste it in here, boom. And you'll see when we compile this, we can even copy this, paste it into Huff here. Oops, I forgot the B at the end. You'll see it's the exact same code as what we got before. Same function selectors, same everything. It's just a bit of syntactic sugar to make it easier for us to auto-calculate those function signatures. All right, this is great. So now we have our function dispatching. We've got a little interface to make function dispatching a little bit easier, working with our function selectors. Now we have our two main functions that we get to work with. We have our set number of horses and we have our get number of horses. These are going to be the jump destinations for our opcode to go ahead and work with. So let's actually do the set number of horses or update number of horses first. And the reason that we're going to do this one first is because one of the first things that we need to do is we actually need to store this value in a storage slot. So a quick refresher on storage. When we work with storage, we can think of storage as a giant array. A giant array that when the execution of our transaction finishes, it stays. Right? And we have variables in our contracts in Solidity that get mapped to some storage slot that stays and persists. Booleans get mapped, favorite numbers get mapped, and they all get mapped in some type of bytes 32 structure. And mappings are a little bit tricky, where the way they work is they have little hashing algorithms that assign their values to a storage slot depending on what slot that array is assigned to. So like, let's say, in this example here, my array is at slot 2 in storage. The first value, the value at slot 0 in my array is going to be at kcac 256 of 2 of whatever the value is. So they use a hashing algorithm to put the data of arrays and mappings at slots in storage that are hopefully nobody else is going to use. Constants do not go in storage, nor do memory variables, of course. So when we're working with storage and we want to update storage, we got to do a couple things here. So to set our number of horses, we got to do a few things. We're going to, number one, have to give it a storage pointer or a storage slot. And then number two, call the store opcode to store the value. And that's pretty much it. So our set number of horses needs to do these two things. And then once it's in storage, we'll essentially give it a little slot here, which will represent the num of horses, right? And this will permanently be in storage forever at whatever storage slot we give it. And once we do this, and once we write both of these, then we can write some tests that will compare our Huff implementation against our Solidity implementation, and we'll see that they both do exactly the same thing, which will be really exciting. So we're almost there. We're getting actually really close. We're actually almost done with this Huff code base already. Let's set number of horses. Let's update the number of horses here. So let's do that. So in order for us to store this data is we're going to have to use the store opcode. So if we look for the store opcode, this is the opcode that's responsible for storing data to storage. And once again, it has a stack input here, and it actually has no stack output. So it's just going to pop the first two items off the stack and stick those values into storage. So the top of the stack is going to be a 32-byte key in storage, and then the value to store. So the top of the stack is going to tell us where to put this, basically. Are we going to put this at index 1 in storage? Are we going to put this at index 2 in storage? At index 3 in storage? And then, of course, instead of 1, 2, 3, these are going to be bytes, binary here. But where is this number of horses variables going to belong? Slot 1, slot 2, slot 3, etc. And then the value to store, obviously, is going to be the number of horses that we want to put in here. Actually, we have to do one more thing. We have to get the value to store from call data, and then we have to store it. Sorry. So we have to get a storage slot, get the value the user called to store, and then store the opcode. So in horse store, update number of horses. Maybe they put in like 2, right? We have to say, okay, well, the number of horses storage slot is X. You want to store number 2. Okay, let's store number 2 at storage slot X. Great. So let's go ahead and let's do that. So how do we get the storage slot for number of horses? Well, we could do this a number of ways, right? We could hard code it. We could just say, okay, at 0x, 80 or something, that's going to be where we store this storage slot. And we 100% could do this, but Huff actually makes working with storage a little bit easier. This is another one of Huff's few abstractions that they have. They have this keyword called free storage pointer, where it essentially is just a counter for what storage slots are open. So if we, in our code base here, we scroll to the top, if we define a constant variable, call it number of horses storage slot equals free storage pointer like this, this will just assign number of horses storage slot to slot 0, to whatever slot is open. If we do a new one, number of horses storage slot 2, this would assign it to 1. So this free storage pointer is just a counter essentially, which says, okay, here's the slot that's currently open in storage right now. Because remember, every storage slot is going to be 32 bytes. So number of horses slot, free storage pointer. We could also just say it's 0x00. We could hard code it like that. But when working with storage, it's usually best to use the syntax in Huff. So cool. So now we're saying, okay, in storage, sorry, it actually increments from 0, not from 1. In storage, at slot 0, that's where we're going to put the number of horses. Not slot 1, not slot 2, not slot 576, at slot 0. So anytime somebody looks at this smart contract, looks at storage slot 0, that's where the horse number is going to be stored. And that's exactly how Solidity works. When Solidity sees the first variable in a Solidity contract, it automatically assigns this to slot number 0. So great. So now we have a storage slot. So we're probably going to want to use this storage slot. Now to reference this storage slot 0 in our code, down in here, we do this syntax like this. We just put it in between these brackets. These brackets here will basically say, okay, I'm going to put onto the stack. It basically is doing a push of this value onto the stack. So I'm going to push that 0, that storage slot pointer. For your notes, you can put number of horses storage slot. You can do 0x00. You can do PTR for a pointer to that storage slot. Whatever you want to do. This is essentially saying at the 0th index, what this number is returning is it's returning the number 0. We're saying, hey, number of horses is an index 0. Great. Number of horses storage slot is 0. So this is just the index in storage where it is, or the pointer of where that value is. And this is where we're going to want to store our data. And if we go back to the store opcode, we're going to need the 32-byte key in storage. Check. We just got that. Now we also need the value, and we need the key on top of the value. So we should do the value first because that's how stack works. So these are actually kind of out of order. Boop, boop. So we actually need to get the value from the call data first so that the key is on top of it. So the question is now, okay, how do we get the value we want to update from the call data? Well, remember in Remix, we grabbed this chunk right here, which was kind of a little demo of what's going to be sent. So again, the first 4 bytes is going to be the function selector. And then the next is going to be the call data associated with the parameters of that function. For us, the uint256. When we did this in Remix, this was the wrong function selector, but if we did this Remix, if I change this to 7, update horses, let me look at the transactions, scroll to the bottom, input here, let me copy that, show you what that one is. Boom. This is the call data that's going to be returned. Once again, we have the function selector at the beginning, and then all of this is the encoded 7. So this is the hex of the number 7. So everything after the first 4 bytes, these 32 bytes here, is going to be the number that we want to update this to. So how do we do that? Well, we already know how to get call data because we learned about call data load. Call data load, right? So call data load, what does it do again? Okay, the byte offset in the call data is the input, and the output is going to be the 32 byte value starting from the given offset of the data. Okay, great. So if this is our call data, right, because the call data is going to be the same no matter what, it's not going to change, we want to get rid of the first 4 bytes. We would set the byte offset, our stack input, to be the first 4 bytes. Because remember, the function selector is going to be 1, 2, 3, 4 bytes. And the rest of this is going to be the 32 bytes associated with the call. So we just saw that in Remix. Let me actually copy the Remix one because that's using the correct function selector. So what we would do is we'd push 0x04 onto the stack. So essentially 4. And then we would do call data load. And this call data load is going to just add on the, if we called with 7, it's just going to be that 7. So this is going to be essentially the call data minus function selector, or you can just say this is going to be the input value, whatever you want to call it. So now we have the input that we want to actually store, or the value, whatever you want. Then we put the number of horses storage slot on here. So we would have storage slot input. So just storage slot. I like that a little bit better. Storage slot or value. Let's do value. I like value a little bit better. Storage slot and value. Then we can call the store opcode. Because what's this going to do? Again, store. It's going to say, okay, at the top of the stack is the 32 byte key in storage. That's our storage slot. And right underneath it is going to be the value to store. That's going to be our input 7. So we're just going to call store. And then importantly, we're then going to call stop. If you don't call stop here, the code will continue to execute. If the opcodes for get number of horses are right after, it'll also do get number of horses, which kind of would be a waste of gas. And we don't want to waste gas. So we're going to stop here. So the stop opcode costs 0 gas and it just stops the transaction. That's it. It doesn't revert. It's a successful transaction, but the transaction is just done. It's just the end of the transaction. Cool. So this should be a working macro to actually update the number of horses in storage. Well, let's compile this to make sure it actually compiles. It sure does. This is the runtime code. So let me copy the runtime code. Let's bring it over to the playground to test this out. And don't worry, I'm going to show you a better way to test these pretty soon. And now if we look in our opcodes list to the right here, we now have this store opcode at the bottom. Okay, exciting. All right, so let's come up with some valid input data. So this should be valid input call data to update the storage to 7, right? Because we have the function selector for update number of horses. And then the parameter data here is the number 7 encoded. So if I grab that and I stick it into the hex call data of our playground here and then hit run, we now can rip through and see our memory and stack as we do this. And we're going to show you a way to do this in Foundry as well. So let's go ahead and step into this. We kind of already know what some of these are doing. It looks like we're pushing the function selector, we're comparing it, we're pushing the other function selector, we're jumping if, and it looks like we went ahead and jumped, right? That's why we shot down here as I was pressing the buttons, because we've identified a correct function selector. Now we're doing push 4, which is what this push 4 is going to be, this push 4 right here. Then we're doing our call data load, which is going to be this part right here. Push 0, because our number of horses storage slot is actually storage slot 0, right? Push 0. And then we do an store exactly as we just thought. So if we scroll down, right now on the stack is 0, 7, and the function selector. Oh, I guess the function selector is technically on the stack when we do this as well, but that's okay. I didn't put it in the notes here. So 0, 7 in the function selector. So storage slot, value, and then also the function selector. And when we hit next here, it should store that 7 into this little storage bit here. So I'm going to hit next. Now we're at the stop, and we see the value 7 is in storage slot 0. And if we hit next, now that we're at the stop, we've actually ended because stop ends execution. You can see there's actually another jump test after the stop that we didn't go to. And this other jump test is going to be the read number of horses code. We don't want it to read the number of horses. We want it to just stop. We want it to finish executing. So that's why this is here. This stop is actually really, really important, because if this next function in your code base was like update number of horses by 2, whenever you update number of horses, it would double it, or it would do whatever this next function is. And we don't want it to do that. So awesome. So we learned after the function has been dispatched, run the function and then stop. And when we decompile the Solidity smart contract, this code right here is nearly identical to what this function is doing in Solidity. These two are doing almost exactly the same things. Solidity has a couple of more guardrails, a couple more opcodes that I'll walk you through in a minute. But essentially, you've just learned how to build a function in Huff, and essentially in raw bytecodes. This is so exciting. All right, nice. Let's keep it going. So now we only have one thing left to do. Let's just figure out how to read the number, and then we can write some tests, and I'll show you how to debug Huff a lot better, a lot easier than copying and pasting the output into this playground over here. So, final thing, get number of horses. We want to read the number of horses from this storage slot that we came up with up here. So, how are we gonna do that? Well, number one, get the storage slot. Number two, load the value of that slot into memory. And then three, return. So there's two keywords two opcodes that we're going to work with here, and they're going to be sload. You've probably definitely heard of this before. This is where we load from storage. This is the read from storage. This is a very gas expensive opcode. At the top of the stack is going to be the 32-byte key in storage. This is the index in storage we want to read from. And the output we get from this on the stack is going to be the value stored in that slot. So essentially at the top of our stack, we're going to have the number 0, or the index in storage, or the key in storage, if you will. We're going to run the sload. It's going to pop this off. EVM is going to go, okay, let's look at storage. What's at slot 0? It's the number of horses. Great, let's stick that onto the stack. And that's it. That's how that's going to work. The other opcode that we're going to look at here is actually the return opcode. So this halts execution, returning output data. This is essentially the same thing as stop, except it returns some data. And it returns data from memory, not from the stack. So if we want to return a value to the user, we have to first load it into memory and then return it out of memory with the return keyword. So to add stuff to memory, we're going to use the mstore, which is essentially the same as store, but instead we're going to be using mstore. So it's like memory storage. Because again, you can think of memory as basically the same thing as storage, just a giant array, but the difference is it deletes at the end of the transaction. All right, cool. So first thing, let's get that storage slot. Well, we already know how to do that with this notation here. So this is going to be the key or the index or whatever you want to call it. Then all we have to do with this key is call sload, because the sload, that's all it needs, is the key. So we're saying, hey, at index 0, give us the number of horses. So we go sload. And now on our stack, we have the value. We have the number of horses on our stack now. So now in order for us to return it, we got to stick it into memory first. So this is where we're going to call mstore, which is right here. So mstore takes an offset and a value. So the offset is going to be the offset in memory in bytes. And you can think of this again as kind of like the index in memory. So are we looking at index 0, index 1, index 2, index 3, etc.? But instead of index, it's like the offset in bytes. So, but just, you can kind of just think of it as like the index of memory. So we don't have anything in memory, so we can just say, okay, 0x00. So we're going to stick it at the 0th index in memory, or the 0th offset. So now we have 0, comma value. Now that the top of the stack is the offset and right underneath is the value, we can just call mstore. And now we pop both of those off. And now we have nothing in the stack, but our memory looks like this now. So this is kind of the hard part of working with opcodes and working with Huff. There's a lot of data structures you will have a hard time keeping track of when you're writing assembly. What's on the stack? What's in memory? What's in storage? What's in this? What's in that? This is why everyone codes in a higher level programming language like Solidity. When you have a ton of stuff in memory, a ton of stuff on the stack, it can get very difficult conceptually for you to keep track of all this stuff. But once we have our value, our number of horses stored in memory, what we can do then is actually return it. And the return keyword takes an offset and a size. So this is going to be the offset in memory. For us, it's going to be 0 because we put it in the 0th slot in memory. And then the size in bytes is actually going to be 20. And that needs to be where? That needs to be below the offset. So we're going to do that one first because that's how stacks work. So The size is going to be how much of the memory data we're going to copy. 0x20 is going to be equal to 32 bytes. 0x20 equals 32 bytes, right? If we do cast to base 0x20 dec, we get 32. So we're going to say, okay, we're going to have something in memory slot 0, which we just stored right before this. It's going to be 32 bytes long because it's just a number, right? That's all we stored. And then we're going to run return. And this again is going to pop everything off the stack. And it's going to return what's in memory. And what's cool is it's going to exit the current context successfully, which again, as you know, it's basically exactly like this in any function, like this keyword right here. And that's it. So let's try compiling this. Great, compiling successfully. So now let's finally stick this into the playground and see end to end how this would work for reading some data. So now we actually don't need the set number of horses function selector. We need the read number of horses function selector. And we actually don't need any other call data other than the read, because in our read code base, we never access any other call data outside of the function selector in our dispatcher. So I know I'm saying a lot of words, but let's paste it in here and let's run it. Let's step through this. And if you want to scroll down and see what the slots look like as we do this, you can do so. So we scroll up, some of our beginner stuff, the SHR that tells me that we're in the function dispatching section. Okay, there's the equals, there's the jump if. We didn't jump, so we're going to compare it to the next one. Here's a second jump if. And if this is wrong, if this function selector is wrong, we are just going to hit the revert. If it's right, we're going to jump down to the section down here. And we sure do. We jump down to the section down here. And we can even see kind of the rest of the opcodes where we're going to push 0. We're going to S load. We're going to load from storage. So after that opcode, if I scroll down, we now see on the stack is 7 because actually, well, this is still actually left over from the last time I ran this. So the playground's really cool where the storage and the contract will actually stay. So I have 7 in there. If you're running this for the first time, you'll probably have 0 in there. But now we've loaded that 7 into our stack. We now need to store it in memory. So after we run this mstore, I'm going to hit step into. So we just ran this mstore. So if I scroll down, we now see in memory, we have the 7 stored here in memory. And now we're going to push 20, push 0, and return, which is going to say, okay, start from 0 in memory and return all 20 bytes, all 32 bytes or OX20 in hex of memory. And boom, that's exactly what happens. So this is incredibly exciting because you just wrote your first Huff smart contract. And in doing so, you learned about a ton of different opcodes and a ton about how the EVM works. Let's do a quick refresher of all the stuff we learned, and then we'll go on and we'll write some differential tests here. We learned every single smart contract, doesn't matter if it's written in Viper, in Solidity, in Huff, pretty much needs to start with a function dispatcher. And this is when you check the call data sent to the smart contract for the function selectors. Once you find a matching function selector, you basically route the call to whatever lump of code is associated with that function selector. We learned about the jump if opcode, where we can jump if some value on the stack is true. We learned how to work with storage slots. We learned how to S store. We learned how to S load. We learned what memory was, and we basically just learned how to write a smart contract in raw opcodes. This is fantastic. If you're kind of feeling overwhelmed right now, now's a great time to go take a break, go for a walk, grab a coffee, and come back to this. This is heavy stuff. And the Huff docs do a great job as supplemental information on understanding the EVM, showing pictures, etc. If any of this doesn't make sense to you, tinker with it. Try something else. We are not going to show you the Huff debugger, so you do not need to install HEVM. However, if you like to, feel free to go ahead, try HEVM with the Huff debugger. Although I'm going to tell you right now, You will run into some hurdles installing HEVM, installing potentially Nix, and working with the Huff debugger. Use at your own risk, essentially, and I'm not going to be showing you how to work with it. Instead, we're going to be showing you how to write Foundry tests that work with Huff so that you can basically debug everything through Foundry. Cool? Cool. Okay, well, we are at a phenomenal place. We've learned a ton already. We've built a smart contract in Huff. We have the equivalent Solidity over here. And now you can probably see why nobody would ever want to write their smart contracts in assembly or in Huff. Writing opcode by opcode is a whole lot more tedious than writing a higher level programming language like Solidity. Sure, you might be more gas efficient, but it's kind of 5 times as long to do something that you can do in Solidity in like 2 seconds. But to make sure these two code bases are doing the same thing, we can write some differential tests or some differential fuzzing, etc. And once we write these tests to prove they're doing the same thing, then we're going to break down exactly what's going on in the Solidity code, opcode by opcode. And you're going to see a whole lot of comparisons, a whole lot of parallels to what we just did in Huff. So what we're going to do to get started is we're going to create a new folder in here, and we're just going to call it V1 of our tests. And this is where we're going to write our V1 tests. Now I'm going to make a file called base test v1.t.sol. And this is actually going to have all of the tests that we want for both Huff and for Solidity. We're going to have a Solidity version of the test inherit this one, and a Huff version of the test inherit this one, so that we are 100% sure both smart contracts are running on the exact same tests. You'll see what that looks like in just a minute. So let's go ahead and let's write some tests here. And I'm going to go kind of quick because at this point you should be pretty good at writing this stuff. It's going to be an abstract contract so that when we run the tests, you have to inherit this contract in order for a test to actually run. Base test v1 is test. So feel free to follow along with me, or if you want to just copy paste, you can do that too. But I highly recommend you writing the test because getting good at writing these differential tests will be really, really helpful for you. So we're going to import horse store. This is going to be the Solidity src horse store v1 horse store.sol. Import test console2 from forge std test.sol. Abstract contract base v1 test is test. Okay, great. We're going to have a horse store, public horse store, function setup, public. And we're going to make this virtual because we're actually going to override this in a bit, and you'll see why. We're going to say horse store equals new horse store. So this is pretty typical of Solidity, but what about for Huff? Well, let's finish writing this. Let's actually just write one test here. We'll say function test read value public uint256 initial equals horse store dot read number of horses. Assert equal should be 0. Equal. So now if we run forge test, this actually won't run. This will do a whole lot of nothing. Why? Well, because we are in an abstract contract. So what we're going to do is we're going to make another one called horse store sulk.t.sol. And this is where we'll do pretty much nothing different. GPL 3 only, 0.8.20, contract horse store sulk is base test v1, import base test v1 from there, and boom. And now that we actually have a contract that's not an abstract contract, now if we run forge test, the test will actually run, ta-da, and it passed. And it's because it's inheriting all the tests from in here, the one test and the setup and everything. Now what we want to do is we want to actually create a new file called horse store huff.t.sol. And we want to put this into v1, excuse me. And I'm actually going to copy paste this one. I'm going to copy paste our horse store sulk. We're going to call this horse store huff. And the only difference that we're going to do is we're going to do a function setup public override. And instead of deploying horse store equals new horse store Solidity, this is where we're going to have horse store equals the Huff edition. And this way, both our Solidity smart contract and our Huff smart contract will run on the exact same tests. Pretty badass, right? So in order for us to deploy a Huff smart contract in Foundry, we need to use this Foundry Huff Foundry extension. And you can find a link to this in the GitHub repo associated with this course. So if we scroll down, you obviously need Huff installed, but to install this in Foundry, you just run this forge install Huff language Foundry Huff. So let's come back over here. Let's install this. Oops. --no-commit. And what this is going to do on the back end behind the scenes is whenever we deploy a Huff smart contract, it's actually going to basically run Huff C, blah, blah, the smart contract, paste it into some file, and then Foundry is going to read the binary and use that to deploy a smart contract. So since Foundry is going to run the Huff C command, we have to do FFI equals true. Now remember, anytime you do FFI equals true, you're basically giving Foundry permission to do a whole lot of crazy stuff. So just always keep that in mind whenever you set FFI to true. And then additionally, we're going to need to add some remappings. We're going to say Foundry Huff equals lib/Foundry Huff/src. And now that we have Foundry Huff installed, we're going to import the Huff deployer. So import Huff deployer from Foundry Huff deployer.sol, like this. And what we can do is we can actually deploy our Huff smart contract. So you can actually go ahead and read the Huff Solidity codebase if you want to really know how it's working. But I'm just going to pretty much give you the shortcut here. We're going to say horse store equals Huff deployer.config. It's one of the first things you pretty much always have to do. .deploy, and this is where you actually give it the file path of the horse store. So for us, we're going to say string public constant horse store Huff location equals, and the syntax is a little bit weird. It assumes everything's in src, so you don't have to put src, but you do have to put the file path, but without Huff, without the .huff. So it's a little bit confusing, but so no src, horse store v1/horse store. So we're not doing src/, it just assumes it's there. And we're also not doing .huff. It assumes it's looking for a .huff file. So we'll do horse store equals Huff deployer.config.deploy horse store Huff location. And then we have to wrap this all up into horse store like this. Oops, like this. And then we also need to import horse store from base test v1.t.sol. And that's it. And once we have this set up like this, what's going to happen is we're going to run two suites of tests, horse store Huff and horse store sulk, and they're both going to run on every single test that we put in the base test. So now if we run forge test, we should see that test run twice because it's happening in two different folders or two different files. We ran into a bug here. Great. The error was only on the Huff one. So we can actually do forge test -- match path star Huff star -- actually, we can just do that. So this will only run forge tests on the files with Huff and this one test that didn't pass. So let's actually do that again with -1234. And we'll see why I failed here. And we're getting this error not activated. That usually means it's defaulting to the wrong EVM version. So let's do EVM version equals Shanghai in the foundry.toml. And let's run this again and a pass. So a lot of the Foundry tests actually default to Paris. So we just need to put in, hey, we want to use the latest and greatest Shanghai, which has push 0, ta-da, and we pass. Hooray. So what did we just prove? Okay, well, we just proved something pretty simple, actually. In our base test, we just proved that at storage slot 0, both of these start with a value of 0. Which is pretty trivial, makes a lot of sense. But we can go even deeper than that. So we can run this same test again. So I'm going to hit up a couple times. And I can also do --mt, or excuse me, --debug, paste the test name, and now run it. And now we'll get popped into the debugger where we will be able to go opcode by opcode. We would see exactly what we would see if we were calling the smart contract and we wanted to look directly at the bytes data. So pretty cool stuff. You can see at the bottom all the different little commands you can use. So I'm just going to hit J a bunch, which stands for next opcode, and we'll be able to go opcode by opcode in here. Now, kind of got to zoom out a lot for this for you to get a good eye of what's going on here. It might be a little bit small here as you're watching, but yeah, that's kind of just the way it is. But if we kind of scroll down in the code base here, there's a whole lot of setup that the test needs to do that we can kind of ignore. And this kind of is one of the hard parts of working with the debugger in Foundry is you want to get to that call stack of the actual contract. And we can see at the top the address that we're working with. And when I hit J once more, it looks like this is where we finally start working with our smart contract, our actual test. And that can be kind of tricky to tell when you're actually in the smart contract, but looking at the function selectors here, right? So we see some familiar stuff. We see a push 4, and I know it's kind of really small. We see a push 4 equals push 2, push 4 with some function selectors that we recognize. Now we can pretty easily say, okay, it looks like we're in the right code. It looks like we're making a call to our smart contract. So now if you wanted, you can literally go opcode by opcode. You can see what's in the stack. You can see what's in memory. And if you run into an issue with debugging a Huff smart contract, you could use the Foundry debugger to actually walk opcode by opcode through. So we can actually even see what this one's doing, right? So we have a call data load. After the call data load, it looks like this is what's in the stack. And I know it's super, super, super small, but it looks like it's just E0, 26, C0, 17. So that's going to be the function selector, and then 0 for the rest of the data. We have the right shift, dupe 1. We're checking if the function selectors match, jump if. Okay, they didn't match. Okay, we're going to go try the second function selector. Looks like they did match. Great. We're in the part of the code where we're reading the number of horses. We're S loading it, right? And so right when we do S load, it's kind of uninteresting because we S loaded 0 in, but then we load that into memory and then we return, right? And then it's running the rest of the test, which is going to be some like assert equals and stuff. So I know that was really small to see. So instead of doing the read, when we test the update in our tests here, we can put a number that's easier for us to see, like, you know, maybe like 777 or something. So, but okay, cool. So this works great. Test read value works great. Cool. So let's now do function test write value, right? And this is just where we're going to update the number of horses. So we'll say uint 256, number of horses equals 777. Horse store dot update horse number, because the function selector for the Solidity and the Huff is going to be exactly the same number of horses. And then we can say assert equal horse store dot read number of horses should be equal to the number of horses. Now, if we pull up this again, let's run our test again, forge test -- match path Huff -- debug test write value. We'll be able to walk through the opcodes and hopefully we'll be able to spot this, what is it? This 777. So if I pull up a new terminal here real quick and do cast to base 777 hex, we're looking for a 0x309. That's going to be the 777. So I'm going to zoom out a little bit. Sorry, I know it's super tiny. I'm going to hold down J, and we're going to look for function selectors that match or that 777. Remember, all of these opcodes are like Foundry setup, right? The test has to get set up. The tests have to get called. We're deploying our Huff. We're doing a whole bunch of stuff here. And okay, cool. Looks like we jumped to the contract. There's some function selectors here that I recognize. Okay, cool. So we have a push 4 equals push 2 jump if jump dest. It looks like we did indeed jump. And by here in the opcodes at this jump destination, we should be at the set number of horses jump destination right here. So this jump destination here should be the beginning of our set number of horses. Okay, we have a push call data load, push 4 call data load. That looks pretty promising, right? Push 4 call data load. That looks good. Then we do push 0 s store. So let's look at our stack right now. So at the top of the stack is 0. The second piece on the stack is going to be 309. Oh, okay. So at the bottom of the stack, we have, it looks like a function selector. And then once we did call data load, it looks like we see 309, which is going to be that 777. So when we called store with 0 and 777, we're basically saying we want to store at the 0th slot, the 777, and then we're going to stop, and that's the end of the call, right? And then we're going to do some asserts. That's going to be what the rest of these opcodes are. So I know that was kind of quick, and there was a lot to that, but I want you to play with the debugger a lot, just like we did there, and try to figure out where you are in the execution. Just remember, whenever you run one of these tests, it needs to do all the opcodes associated with the setup, with the getting the values here, with the asserts, etc. Definitely practice using the debugger to actually see, okay, when are we testing 777? Because this will give you the power to actually, read opcodes. So just try to recognize where the 777 is, look for that 309 in those opcodes, and then you can be like, boom, I found it. I'm an opcode wizard, Jesus. But okay, cool. So we've written 2 real minimal tests. I'm just going to leave them like this for now because reading and writing is really all that we're doing. However, if you look at the Git repo associated with this course, we do take a slightly different approach, and you can do whatever approach that you want here. In the GitHub repo here, we actually do a little bit more formal differential tests where we actually deploy the Huff, the Yule, and the Sulk version. And then at the bottom, we basically compare them to each other, which is another way to really just make sure that they're the same. And then we use some fuzzing instead of direct values. So we probably would want to do the same thing here. So we would do U and 256 number of horses as a fuzzing parameter, do the exact same thing, right? And now we can just run forge test. And now we'll fuzz both of these contracts so that they are looking good and they look equal. So Sulk looks good, passes everything. Huff looks good, passes everything. So one more thing, in this Huff, we could do some malicious stuff, right? Set number of horses. What if instead of OX4, we put OX2 in here, right? Now we run the tests. They're probably going to fail, right? And sure enough, they do fail, right? Because it's not the correct offset of the call data. We could put the wrong storage slot in the read, right? Same thing. If we run the tests, this is going to fail again. There's lots of ways to very subtly mess this up and fail your tests, and especially lots of ways for your Huff to go wrong or do something unexpected. This is why if you are going to write low-level assembly, low-level Huff, etc., it's highly, highly recommended you use stateful fuzzing, stateless fuzzing, and maybe even formal verification to prove that your Huff, your low-level code, matches your Solidity code. And later on in the course, of course, we're going to teach you formal verification so that you can actually do what we're working with here. But nice. So now you have a good understanding of how these smart contracts work at a binary level. What we're going to do now is we're going to take this Solidity and we're going to crack it open, and we're going to go opcode by opcode of this Solidity, and we're going to break it down exactly what it's doing. Now that you've been primed with the Huff, this section is actually going to be a lot easier than without the Huff, okay? And if you want to see the breakdowns of these in the GitHub repo associated with this course, I've got some written breakdowns of what every single opcode in this is doing for both the Huff and the Solidity. And you might be surprised, but the Solidity actually is way, way, way bigger and uses a lot more gas, and we'll explain why there's so many more opcodes in Solidity. So this is the part of the course where we're literally going to be ripping through binary. And it's going to be pretty fun because the whole time you're ripping through binary, whenever you're ripping through binary yourself, you're always asking, what is this doing? What is this opcode here for? And that's kind of the fun of being badass with EVM opcodes. You can start to make fun of compilers. You can start to shitpost about compilers on Twitter. Try to do that as little as possible. There's kind of a meme of gas optimizers who always shit talk compilers, but whatever. This will teach you the low level, how this stuff works. And a lot of smart contract developers do want incredibly proficient, incredibly performant assembly chunks of their smart contracts. And only once you know how to use all of these opcodes will that power unlock for you. So we're going to break down a Solidity contract. We're going to deconstruct it ourselves, and you're going to learn exactly how the Solidity compiler works. So go get a coffee because this part's going to get pretty intense. We're going to do a whole lot of reading. And the main thing we want to ask ourselves is, what is the Solidity compiler doing? Why is this opcode here? And we're going to consistently ask that question. But big check mark to ourselves. We have written the horse store in Huff. Huge check mark. We understood where and why this data looks like this. And then how does Remix know to update the number of horses with this data? Well, we learned that too, because it all is about the opcodes. If you're pumped about just learning this much, this far, this is a great time to jump on Twitter and say, holy hell, I'm learning so much about Huff and the EVM, and tag us, tag Cyfrin Updraft, tag me. But yeah, go get a coffee, go get some ice cream, maybe go to the gym, because we're going to get intense by cracking open this Solidity code. Let's do it. All right, and now is the time where we are going to break down all these opcodes in our Solidity smart contract, and then we're going to compare it to the Huff smart contract. So I'm going to go ahead and create a new folder called Breakdowns, where we're going to see exactly what these opcodes do in these smart contracts. So when we compile our horse store.sol and we deploy this in our out folder, we go to horse store.sol, horse store.json. Let's go ahead and let's format this, and let's toggle the word wrap. Let's go ahead and find the opcodes or the bytecode. So here are the opcodes. Here are the opcodes in their binary. And I don't think we have the opcodes in the text in here. Okay, no, we don't have the opcodes in the text in here. That's okay. So what we can do is we can actually copy this, and in our new little breakdowns folder, we're gonna create a new file. We're gonna say sulk breakdowns.c++. This isn't really going to be a C++ file, but the syntax highlighting for C++ is going to be really nice. So we're going to just pretend this is a C++ file here. And I'm going to toggle the word wrap. So here is the sulk binary. Now, every two of these is going to be an opcode. So 60, for example, go back to evm.codes, go to 60, that's going to be push 1. So we could 100% break it down opcode by opcode like that in the binary, but that's kind of a huge pain, and I don't want to do that. So instead, what we're going to do is we're going to go back to the playground, paste it in here, switch over to mnemonic, and then just copy everything in here and paste it like that. Boom. Now we have all the opcodes that are going to get deployed. And this is the only time we're going to be walking through these opcodes is for the Solidity. I also have a breakdown of the Huff opcodes, but that's obviously a lot easier because the Huff is basically just opcodes here. But this is the only time we're going to do a walkthrough of the opcodes. But I do recommend that you try to walk through some small contracts of your own after this section and see if you can understand how the opcodes are working yourself. And so let's break down exactly what all of these opcodes do for our Solidity code here. And let's start from the top. So you will see this exact setup in pretty much every single Solidity smart contract that you work with. 60, 80, 60, 40, 52. This right here is going to be the first section of the contract creation code. Remember how we said that there's 3 sections, right? There's 3 sections. 1, contract creation. There's 2, the runtime, which is what actually gets stored in the blockchain. And then there's 3, which is the metadata, which often is kind of nothing and just tells a lot about the compiler version that was used and any other metadata that you want to store about the smart contract. So the beginning is always going to be the contract creation code, no matter what, right? Because when we deploy this transaction with all of our data, the entry point to our transaction is going to be the first couple of opcodes, right? So the contract creation code is always going to be our entry point. But why do we always see this push 180, push 140 mstore? What is this doing? Well, this first section that you see all the time in Solidity is something known as the free memory pointer. So if we do the little notations here, what is this doing? Well, it's pushing 0x80 onto the stack. Then what's it doing? Then it's pushing 0x40 onto the stack, 0x80 is onto the stack, and then it's doing an mstore. Okay, well, what does mstore do again? If we go back to evm.codes, mstore, offset value, and it pushes that value into memory based off of the offset. So the top is the offset of OX40 and the bottom is OX80. So let's look at a little example of this that I did at an ETH Denver talk a couple of years ago. So we have this push 80, push 40, and then this mstore. So here's what our memory looks like, and here's our starting stack, right? So memory, as we know, is kind of this giant array. And originally, I was showing you it as a giant array of 0, 1, 2, 3, 4, 5, etc. with like indexes. That's not technically correct, right? Technically, it's an offset in bytes. So it could be 0x01, 0x02, 0x03, etc. 0x20 is going to be the 32 bytes. So if we look at memory as this array of 32 bytes, you know, the 0th slot is going to be 0x0. The first slot after the first 32 bytes is going to be 0x20 because 0x20 is the hex of 32 bytes. So 0x0 is the 0 slot, 0x20 is the first slot, 0x40 is the 4th slot, etc. When we do these opcodes in Solidity, push 80, push 40, mstore, we're pushing 80 on the stack, then we push 40 on the stack, and then we store that 0x80 into the 0x40th position. This 0x40 is always a reserved slot in memory for this thing called the free memory pointer. Why do we need to have memory and storage? Well, stack is restricted in size, memory is much bigger, right? Variables are returned from memory, they're not from the stack. We're always gonna have to do stuff with memory. But since we put something in memory here, if we wanna put another value into memory, how do we know where we can put stuff in this memory array? So how do we know what parts of memory are free? We need a way to keep track of what hasn't been taken up in memory, right? So here's another setup of what memory looks like and some opcodes, right? So in memory, 0x0 and 0x20, or the 0th index and the first index in a memory array, are usually reserved for hashing stuff, right? So they're usually reserved for precompiles. They're usually reserved for doing some very specific stuff. So you'll find the Solidity compiler pretty much never puts variables in the 0th or the first index of memory. And in this 0x40 or the second slot or whatever you want to call it, it usually puts this 080, which points over to this slot. This 0x40 is known as the free memory pointer. Whatever value in here is the index that has, quote, free memory, right? So what this is saying, if this is your memory setup, 0 is blank, 1 is blank, 2 is 0x80, 3 is blank, 4 is blank. Whenever you want to say, hey, where's there some free memory for me to stick some variables in, you always check this second index or the 0x40th offset of the memory array. This is basically Solidity saying, hey, you can put some stuff over here. This is what's free. This 0x40 in memory in Solidity is special because of the free memory pointer. And that's important too. Only in Solidity, this is important because in other languages, they might not have a free memory pointer. In Huff, we didn't have a free memory pointer. We decided when we were building Huff, hey, we don't need to care about a free memory pointer because we're kind of barely using memory. We never needed to worry about overriding memory or anything like that. So we just didn't use any free memory pointers. Solidity always uses free memory pointers. Now, you can kind of see as I'm flipping back and forth, if at this 0x40 slot, it said 0x60, that would mean that, hey, the free memory starts at this 0x60 instead of the 0x80. Every time we add something to memory, we're going to update this to say, hey, the free memory pointer is now plus 32 bytes, or just point to whatever slot in memory is finally free. We can look at an example of this of, okay, let's say we have a uint256, 2 equals 2. We have a value that we need to store into memory. We need to mstore this into memory. One of the first things that we're going to do is we're actually going to first mload the free memory pointer and basically check at the free memory pointer's location, hey, where's their free memory? If it's 0x80, we know, okay, there's free memory at 0x80. We can put our memory variable 2 in there. And that's exactly what we do in this example. We put OX02 in that location. And then the free memory pointer is then going to update. Now this spot has something in it, so it's no longer free. The free memory pointer is going to say, okay, now the next 32 bytes is where free memory starts, which is at 0x6a, which is the hex of 128 plus 32, whatever that maths out to be. So this is how the free memory pointer works in Solidity. It's always just pointing to where the next available block is. This is actually very different from how Viper works, and we'll see how Viper works in a little bit. To recap, Solidity works with this thing called the free memory pointer. And this free memory pointer is really great because it allows Solidity to always keep track of where in memory they can stick something new. So what they do is they go, hey, this is free. Let's stick something in there. And then let's update this 0x40 to be a new free memory pointer. That's how the free memory pointer works. So whenever you work with Solidity, you are always going to see this being the starting chunk of code. And basically this is just saying, okay, at location 0x40 is 0x80. So you'll see whenever Solidity wants to load something into memory, it's going to first load the free memory pointer. It's going to use that to be the index of the new value that they put in memory. And then they're going to update the free memory pointer. And you'll actually see that in the code as we move along. No matter what, contract creation code, contract runtime code, pretty much will always start with the free memory pointer. Great. Okay, so now we know about the free memory pointer. What comes next? Okay, let's start going opcode by opcode. So what's this chunk do? That's usually a good question when working with opcodes. We can just say, hey, let's go opcode by opcode. What's this chunk do? Well, let's read this, let's annotate this, and let's figure it out. Okay, so call value. Okay, this isn't an opcode we've seen before. Let's go to evm.code, see what this is. What does this do? There's no stack input. It's worth 2 gas. All it does is give a stack output. Value, the value of the current call way. So this call value is checking the message.value and putting that onto the stack. So if you send any value with your call, it'll push it onto the stack here. We don't have a constructor here though. We don't have a payable constructor. How could you put any value into the contract deployment if you don't have a payable constructor? That's weird. Well, okay, so this could be 0, this could be 50, whatever. Okay, then we have a dupe one. We've seen this one before. It means we're going to duplicate it. So message.value, message.value. Okay, then we have an is0. Oh, this is a new one. What does is0 do? Okay, let's go see it. Is0. Stack input is A, and the output is A equals A. 1 if A is 0, 0 if otherwise. Oh, so we have a little Boolean here. So there's an input to the stack and an output to the stack. So it's going to pop message.value off, check if it's 0, and then it's going to return message.value equals 0, and then message.value is still going to be underneath it. So now we have this Boolean of 0 or 1, and we have message.value. Okay, it's still not clear to me what this chunk of code is doing. Let's keep going. So next, all right, push 0x0e. Okay, we know what that does. That just pushes 0x0e. And then we have the rest of the stack stay the same because it's a stack, obviously. Oh, okay, now we have a jump if. Okay, I need a quick reminder. How does jump if work again? Okay, so the top of the stack input is going to be the counter, and then B is going to be the true false. So 0x0e is going to be the program counter. Okay. And then the next is going to be the true false. So it's going to jump if message.value does equal 0. And so is there any output to jump if? No, there's no output. So the only thing left on the stack would be message.value. So this, it looks like it's doing a jump. It looks like it's doing a jump if somebody sent some value. So this is saying if someone sent value with this call, jump to the 0x0e program counter / jump dest. Okay. So it's saying if the value is 0, we're going to jump someplace. I'm not exactly sure where we're going to jump, but let's keep reading because I secretly know what's coming next. So if we don't jump, that means message.value is not equal to 0. So we have message.value now, because we just did a push 0. We have a dupe 1, which means we're going to do 0x00, 0x00, message.value. And then, whoa, and then a revert? Well, what's the revert opcode do again? Let's go see, revert. Offset size, so message.value is going to be on the stack, and it's going to revert. So we now know what this chunk of code does. The whole thing. We know exactly what this does. So if someone sent value to this call, no, sorry, we don't jump there. Sorry. If somebody sent value to this call, revert. Otherwise, jump to continue execution. So this chunk of code here in our contract creation, we're actually checking to see if somebody sent value with the contract deployment. If somebody did, it'll actually revert. And we can actually see that, right, in our test, in our soak test, in our base test here. If we do a new horse store and we do message.value, we do value of 7 here, it actually doesn't even let us compile because it's saying, hey, you can't put value in with your non-payable constructor. So if you tried to send this transaction, deploy this horse store contract, sending value, it would revert. And our Foundry script doesn't even compile because Foundry's going, hey, that's going to revert always. Don't do that. That's dumb. So cool. And if we wanted to see the jump destination, we could come back here. We could do run with no value. We could jump in here, push, 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 call, 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 jump if. We're at the 0A program counter. What did we say it was going to jump to? Okay, 0xe program counter. Step into, and that's actually the jump test right after the revert. That's kind of the hard part of doing the comments like this. It's a little bit hard to see what the program counter looks like, but the EVM.codes playground has it really well. 0E is right here. That's the jump test, and it's actually just right after this revert. So this jump test right here is where it'll jump to. So basically just skips over this revert. So this is the jump test if message.value equals 0. Cool. So now we continue the call. So what was the value before we jumped? Okay, it was message.value. So that's what we're going to start with here too. And oh, we run the pop-up code. So we're just going to go ahead and pop it right off. So we're going to push 0x on. Okay, that makes sense. We're going to dupe it. That's no problem. We're going to push. We know what that is as well. I'm going to do lowercase here just because I want it to match what my opcodes look like. We're going to push 0. We know what that is as well. It's going to look like that. Code copy. Oh, okay. I told you about this opcode, but we haven't actually seen it. Makes sense that we see a code copy because what are we doing? Well, we're copying our code to the blockchain. So what is this code copy? Okay, so it takes 3 stack inputs, destination offset, offset and size, and no input. So we have 1, 2, 3, 4 things on the stack right now. So these 3 are going to get popped off for this code copy. And what do we have? Okay, the top of the stack is going to be the destination offset. So the byte offset in the memory where the result will be copied. So we're actually going to copy this into memory. So byte offset in memory where the result will be copied. So we're going to start at 0. Then what's the next one? Offset. Byte offset in the code to copy. So we're going to actually start at 0x001b. That's a little weird. Well, what does that mean? Well, this is actually a little bit tricky too, but what this is saying is in all of this code, we're actually not going to copy all of this code onto the blockchain, right? We're not going to copy this stuff at the top, which makes sense. We only want to store the runtime onto the blockchain, right? So this code up here is telling us how to store the contract on chain. And the code later on is going to be how to actually work with the chain. And spoiler alert, this invalid here signals the end of the contract creation section of the binary. So I know from cheating a little bit that this 0x001b is actually pointing to the code down here. This stands for, if we do a little cast to base, decimal is 27. We can actually look at that. And if we do a little counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I might have double counted something. This is the 27th byte offset in the code we need to copy, starting from down here. And then the last bit is the byte size to copy. So OX5A. So we can do a little cast there too. So we're going to copy the next 156 bytes, which should probably just be the rest of the opcodes, right? But we're going to copy this into memory. So this code copy bit is now, we're going to take those three. Our stack is just going to be this, but now our memory is going to be basically like the runtime code, because that's what we just copied into memory with this code copy opcode. Then we're going to do a little push 0. It's going to be 0x00, 0xa5, 0xa5. We're going to return, which is going to return both of these, right? Because return opcode, offset and size, right? So offset, size, and then the invalid opcode doesn't do anything. It just kind of signals to us the end of the contract creation code. So now we know what this does. This basically sticks the runtime code on chain. So we're going to add push 0, and then we're going to return. Remember, the return opcode does what? Return, offset and size of the offset of memory, and then the size in memory. We know that this code copy is 0xa5 long, so we're returning the entire memory, which has all the runtime code, and sticking that on chain as a smart contract. Now, you might be asking a really astute question. The question being, oh, so you're telling me the return opcode actually deploys contracts? It's actually a little bit more nuanced than that. So in EVM.codes, there's actually an opcode called create. And this opcode creates a new contract using the initialization code provided the indicated offset in memory. So you might be going, oh, okay, well then I should probably see the create opcode in this contract creation section, but we don't see that. We just see the return. What's going on here? There's actually another opcode called create2, but same thing. There's no create2 opcode either. We just see the return bit. There's a phenomenal question on Stack Exchange which asks the exact same question. And the answer basically is there's two ways to create contracts. A contract creating a contract, and a transaction that's created by sending nil in the to field of the transaction. You can read more about the different ways contracts are created in the Ethereum yellow paper, but to save you the trouble, this is essentially the answer. There are a few ways to create a contract. One of them is to be setting nil in the to field of the transaction. If it's a contract, using create or create2. So that's why we actually don't see a create or a create2 opcode in this contract initialization or contract creation code. So that's pretty dang cool. And that's how we deploy a smart contract. These are the opcodes that stick our runtime smart contract on chain. So boom, you now know how contract creation code works. Now, what was mind-blowing to me was the first time I learned all this, I was asking a ton of questions. I said, whoa. Why do we do this free memory pointer thing at all? Wouldn't it be more gas efficient to not do that? And the answer is yes, this would be more gas efficient to do that. Okay, well, what else? Okay, we check for some call data over here. Well, wouldn't it be more gas efficient to not do any of that? Well, yes, it would be. We check for some call value over here, some message.value. Would it be more gas efficient then to not do all that? Well, yes, by golly, yes, it would be. So we basically just learned if we added constructor payable, boom, this technically is a more gas efficient smart contract on contract creation because we wouldn't have this check here anymore. And if you want, I challenge you to compile this contract, go check the out, and sure enough, you'll see this section is now missing because adding this constructor payable basically just removes that. And then the rest of this just sticks it on chain. And that's it. You now know, oh my goodness, I can write more optimized code than Solidity. But the thing is, we probably don't want to get rid of this message.value check because this is helpful from a security perspective. What if we fat finger sending $1 million that we'll never get back to this contract? Well, we don't want to do that. So it's good to have these checks in. Yeah, it costs a little bit of gas, but this is like what, 1, 2, 3, 4, 5, 6, 7, 8 opcodes. The 8 opcodes probably isn't going to break the bank. So keep it in there to make you more secure. The free memory pointer on contract creation code, I would argue, okay, yeah, that probably definitely can go. So contract creation code, cha-ching, is done. You've learned a ton so far. So let's keep going. Next. Now we're into the runtime code. All right, runtime code of our smart contract. And as we kind of learned, Solidity is very helpful where it gives us this little invalid opcode to show the difference between sections. But wait, why are there so many invalid codes at the bottom? What the heck is that? Well, we'll come back to that. You'll understand why. But now we're in the runtime code, and this is going to be the entry point of all calls. So in the same way, when we built our Huff, we created this main function, right? Where's our main function? Created this main function as our entry point. In Solidity, the entry point is going to just be whatever opcodes are deployed on chain. So for us, since we copied all of this stuff onto chain and not this stuff, this is going to be our entry point, and this is going to be our runtime code. So our code copy, remember, it started from this section, which is going to be our runtime code. Boom, this is now our entry point for all calls. Make sense? Okay, cool. Well, now that you know a little bit more about how Solidity works, this is going to look super familiar. And you can almost just see this and immediately go, okay, this is the free memory pointer. This is setting up the memory pointer so we can work with memory in a little bit. Great. Next, free memory pointer is now set up. Let's go ahead. Let's go opcode by opcode and figure out what the heck these are doing. So we have some call value here. Okay, we know what this does. This gets the message.value. We learned that before. We're going to do a little dupe one. Okay, we know what that does. Very nice. Is 0. Okay, I know what that does. We're going to say, okay, message.value equals 0. And this is going to be similar to what we did in the contract creation code. But, oh, okay, I recognize this. It's doing the same thing, checking for message.value, but in the contract runtime code. Okay. So now we're going to push 0x0e, message.value equals 0, message.value onto the stack. And now we're going to jump if. So what does jump if take again? Jump if, counter, and b. So what does it do again? Counter is the byte offset, and b is the program counter. So counter, byte offset, counter is the program counter we're going to jump to, and this is the conditional. So we're saying, okay, if message.value is 0, go to 0x0e. Okay, great. We know how to do that. This means that message.value will be left here. So we would jump to 0x0e in the program counter, which is going to be a little bit farther down now because we're in the runtime code here. If message.value equals 0, we're going to jump. And if message.value is not equal is something, looks like we're going to continue. And this looks pretty familiar to us. So let's go ahead. We're going to push 0 onto the stack. It's going to look like that. We're going to dupe 1. And yep, sure enough, we're going to go ahead and revert. So we know what this is doing because we've seen it before. We're basically checking for message.value and if given, reverting. This is a really cool Solidity optimization. So Solidity, basically what Solidity does is it checks all these functions and it goes, okay, are any of these payable? No, that's not payable. No, that's not payable. Okay, I, Solidity, am smart enough to know that no matter what function is called on the smart contract, none of them are payable. And since none of them are payable, whenever anybody sends me a transaction, if they send value, I'm going to revert. So what this is doing is checking the value, checking to see if it's 0. If it is 0, we're going to jump away to someplace else. If it's not 0, we're going to revert. So because I've done this a few times, I know that this is the jump test of this push one up here. So we're going to say if message.value equals 0, start here. I might even put like a little jump to continue or whatever. So do a little continue. Cool. So I know to jump to continue if message.value equals 0. And that's down here. Okay, nice. We have a jump test. Cool. So based off the stack, we started with message.value. So that's what we're going to start down here. And okay, all right, we're going to pop it off right away. Thanks, Solidity. Cool. So not sure what this is doing, but I guess we're going to find out pretty soon. Okay, so now we're going to push 0x04 onto the stack. We're going to do a little call data size, which what does call data size do? I don't think we've seen this one before. Okay, call data size, no stack input. Doesn't look like there's a stack input, but there is a stack output, which is going to be the size, the byte size of the call data. Oh, interesting. So we're going to say this is the call data size 0x04. So if somebody sends some call data that's like 0x something crazy like that, the call data size is going to be really big. But maybe somebody sends some call data that looks like this. This is 1 byte, right? So they would say 0x01, right? It's 1 byte big or 8 bits big. What does it do? Byte size of the call data. Okay, so it would be 1 byte long. So call data size 0x04. Okay, so we're getting the size of the call data. Interesting. What are we doing? Less than LT? What? What is the LT opcode? What is that? I got too many opcodes open. I need to close some of these. T. What is that? LT opcode. Okay, LT, which is shorthand for a less than comparison. It has stack inputs A and B and returns A is smaller than B. So it returns a Boolean again, right? If A is smaller than B, it returns a 1. Otherwise, it returns 0. So true, false, similar to that is 0. So is the call data size smaller than 0x04? So call data size is smaller than 0x04. Now we're going to do a little push 30, call data size 0x04. Uh-oh, and we have another jump if. Whoa, so what is this? So jump if, I always forget jump if. Jump if takes 2, takes the counter, and then the conditional. So the counter and then the conditional. So this is going to be left to blank. So we're going to jump to the program counter or the byte offset at 0x if this is true. Oh, so if the call data is too small, we're going to jump. Oh, okay. So what this is doing is this is checking to see if there is enough call data for a function selector. Because how big is a function selector? So Solidity, once again, is pretty smart here. It looks at this code base and it goes, okay, there's no fallback function. So if anybody sends me data and the data doesn't have a function selector, it doesn't have 4 bytes, it's wrong, right? Because all I can do is these 2 functions, and these 2 functions need a function selector. So Solidity is basically saying, okay, if there's no function selector, if the call data is not even big enough to have a function selector, I'm going to jump. And again, from cheating a little bit, I know where this 0x30 is. It's kind of far down here. I believe it's this one, and we could double check to make sure, but I don't really want to. Call data jump. If call data size less than 0x40, go to call data jump. So that's going to be down here. I think that's this one, call data jump. And this starts off with nothing. And of course, this is pretty obvious what it's going to do. It's going to revert, right? 0, dupe 1, 0, 0, and then revert. So this is a revert jump dest. Oftentimes, Solidity is pretty smart. It goes, hey, there's a couple scenarios where we revert without giving any details about the revert. We're going to leave it as kind of a general revert jump destination. Boom, jump, push 0, duplicate the 0, and then revert with nothing left on the stack. If call data is too small, it's going to jump down here, revert, and the transaction is reverted, and that's it. Cool. So now we know what this is doing. So just in this runtime code, we've already learned a ton. We set up a free memory pointer. We check for message.value. Then we check to see if there's even enough call data for a function selector. We didn't code any of that in Solidity. We didn't code any of that in our Huff. Solidity has all this happening under the hood. It's doing this for us. Good person Solidity looking out for us, making sure we don't shoot ourselves in the foot. Thanks, Solidity. But all right, anyways, let's keep going. So we have this next section of code. Who knows where it stops? Let's find out. Okay, so first we're going to do a little push 0. We love the push 0 opcode. Okay, call data load. We love the call data load. What does this one do again? It's going to take the byte offset in the call data from the stack, and it's going to put back onto the stack the 32 byte value starting from the given offset of the call data. So we're going to take this off the stack and we're going to say 32 bytes of call data is now on the stack, right? Now we're going to say 0x E0, 32 bytes of call data on the stack. Oh, a right shift. Oh, I remember this. Okay. What does this one do again? I think we might be at the function dispatcher of Solidity. Okay, so we're going to shift the value by whatever's on the top of the stack. Okay, so we're going to shift the 32 bytes call data by 0xE0. So let's do that again. Cast to base 0xE0 decimal 224. Whoa, we've seen this before. So we're going to say, yeah, this is the call data from the 0th bytes to the 4th bytes. We've now shifted, and this is probably going to be the function selector. So by doing this, we got the call data. So we're probably doing the function dispatching in Solidity. Remember, we didn't have to write any of that in Solidity here because Solidity does this all under the hood. However, in Huff, we actually coded our own function dispatcher. So now we're actually going to compare our function dispatcher that we wrote to what the Solidity compiler came up with. That's pretty cool. We're going to compare and see whose is better, huh? So call data load, push 0, the right shift, and now we're going to dupe 1. And so instead of call data 04, I'm just going to say func selector, comma func selector, because we're pretty sure this is going to be the function selector. And whoa, I remember this too. What is this? Oh, this is the update number of horses function selector. And now we're pushing that onto the stack in Solidity. Wow. Boom. Function selector, function selector. This looks super familiar to us now that we've written in Huff. Yep, the equals opcode is going to say, okay, does the func selector equal this bit here? We're now going to push on 34. You probably know where this is going. And then we're going to jump if. Almost exactly the same as our Huff, right? So if the function selector equals the function selector for update number of horses, then we're going to jump to program counter 0x34. If function selector equals update number of horses function selector, then call data jump. I'm going to say set number of horses. And we'll get to that jump in a little bit. So this is almost identical to what we wrote in Huff, right? 0, call data load, 0E right shift, dupe 1, push the function selector equals, then a jump destination, and then a jump if. So if this is us function dispatching for the update number of horses, what's next? Well, what's probably next is going to be the read number of horses. Okay, well, let's find out. So, okay, we do a dupe 1. Okay, now we have 2 function selectors in the stack. We're going to do this push here. So this, well, if we go back to our Huff, sure enough, that's the function selector for read number of horses. Oh, look at that though, right? We removed the dupe 1 in our function dispatcher and Solidity still has it. So our function dispatcher is actually a little bit more gas efficient than Solidity's. Nice job, us. Okay, and then we're going to do this equals. So we're going to check if the function selector sent in the call data equals the function selector for read number of horses. And then we're going to push 45. You know where this is going. And then we have a jump if here. So we're basically saying if the func selector equals read number of horses, then we're going to jump to get number of horses. And that's the function dispatcher that Solidity built. Now, what's cool is since this is the end of our function dispatcher, if somebody didn't send us a function selector, we probably should revert. Well, guess what? If the code just keeps going as is, these are the next 4 opcodes it's going to do. So it's going to revert right here if no function selector was set, if no function selector was included. So it'll call jump dest, which, yeah, okay, costs 2 gas, like maybe that's a waste of gas, whatever, but then it'll revert, and that's what we want. Because if it doesn't revert, it would go ahead and actually start executing some code that we might not want it to do. So having this jump destination here after the function dispatching is great because we revert. So this lump of code here, we know what this does. This is function dispatching for read number of horses. And this is going to be dispatching for set number of horses. Ta-da. We're already through more than half the opcodes, and you're doing phenomenally. Let's keep going. But let's go ahead and continue. So now we're at this other jump dest position. This is going to be after we do the function dispatch. This is going to be one of the jump desks, probably one of the jump destinations of one of our function selectors. And we could go back and figure out which one it is, but let's just go ahead and see what this does. And we'll probably figure out what this jump desk is from what it's doing. So this is a jump desk. So this means that we came from this jump if bit or this jump if. So that means we have the function selector. So we're going to push on 43 for some reason. We're going to push on 3F for some reason. And we're going to do this call data size, which we've done before, but let's just double check. Sure enough, this just returns the byte size of the call data. Okay, cool. So again, you know, if we have like function selector and then like a whole bunch of stuff in here, or if we just have the function selector and then nothing, it'll tell us, right? So now we're going to push this. It's a little confusing why we're doing all these pushes onto our stack, but I guess we'll figure out soon. And then we're just going to do a straight up raw jump call. Okay, interesting. So we just pushed a whole bunch of stuff on the stack, and then we're going to do a raw jump. So we haven't done a raw jump before, but all this does is it jumps to the program counter that was most recently on the stack. So we're going to do the jump to the 59 program counter here. And this is going to be way down here. So, okay, I'm going to cheat. So this is the update horse count or update horse number jump dest 1. So again, I cheated a little bit. I've already looked at all the program counters. This is the first jump destination for update horse number. And we're doing all this stuff here, and then we're jumping. And we're actually jumping way down low here to this one. So this is going to be jump or update horse number jump dest 2. So we start here and then we jump down here. And again, I kind of cheated. I've already looked at the program counters. These are a little bit hard to figure out, but like I said, you could pop them into something like EVM codes and see the program counters on the left over here. So now update jump number 2, where we came from up here, and this is our current stack. So same thing, we jump down here and we have this kind of ridiculous stack. So we're not sure what all these pushes are for, but it looks like we're doing more pushes. No worries. So we're pushing 0, we're pushing 0x20. We're going to dupe 3. Now we haven't done this one yet, but this one's pretty obvious. We're going to duplicate the third item on the stack. So we're going to ignore the top, the second one, and then we're going to take the third one and just duplicate it and put it on the top of the stack here. So 0, 1, 2. So we're going to do like this, take this on the stack, and then put the rest of the stack is going to stay the same. Dupe 5, going to do the same thing. 1, 2, 3, 4, 5. So we're going to do the call data size like this, call data size, and then the rest of the stack. And the stack is starting to get kind of big. I'm actually going to take toggle word wrap off here. Sub, this is one we haven't done yet. So let's grab the sub opcode here. And this is going to be a subtraction operation. So we're going to take the top of the stack and subtract it by the second value in the stack. So we're going to do call data size minus 0x04. So I'm just going to take this whole thing, put a little subtraction there instead. So if our call data size was 4 bytes, this would be 0. If our call data is bigger than 4 bytes, this is going to be, you know, some other number, whatever it's bigger by. We have another new one, SLT. This is a signed less than comparison. So basically we're going to do we're going to compare if A is less than B. And if A is less than B, we're going to do a 1 and then 0 otherwise. So we're going to do the same bit here. We're going to say, we're literally just going to copy this whole thing, paste it in here, get rid of the comma. So this is now call data size minus 0x04 is, less than 0x20. So this is actually pretty interesting here, right? We're basically saying, is there more call data than just the function selector, right? Because 0x20 is 32. So if the call data size is 4 bytes, then this is going to be 0 and this is going to be true, right? if the call data size though is a function selector plus data, like a bytes 32, which is what a number would be, then this would be false. So basically we're saying, hey, like, is there more call data than just the function selector right here? And we're doing a little is zero. So remember how is zero works. Is zero takes a and then a equals 0. So we're going to basically just say this equals true. And then everything else. I know this is kind of a big one. But basically we're just saying, hey, is there more call data than just the function selector? And I might even just switch this to more call data than selector. More call data than select. Well, it's technically more call data than 32 bytes, but I'm just gonna say more call data than selector. Now we're gonna do a little push 68, and we have all these pushes that we've been pushing on the stack that we're not sure what they do, but I guess we'll find out. And then we have another jump if. Oh my goodness, there's so many jump ifs. So this is where working with Solidity can be a little bit confusing because there's so many jump ifs and there's so many pushes, and we're like not really sure why it's doing all these pushes and these jumps and etc. But as we know, jump if, we're going to say OX68. We're going to jump if there's more call data than the selector. So right, instead of this is just going to be what? Jump if returns nothing on the stack. So we're just going to delete these. So basically we're going to say we are going to jump dest3 if there is more call data function selector plus 0x20. So function selector plus some other stuff. So it looks like what this is doing, what this lump of code is doing is check to see if there is a value to update the horse number 2, right? Because a number is going to be 32 bytes. Number is going to be 0x20. 0x20 is the hex form of 32. So we're saying, okay, the total call data should be 4 bytes for the function selector and 32 bytes for a horse number. And that's what this lump of code is checking for. And if it is, we're going to jump to this next section, which again, I kind of cheated and I know where it is. Otherwise, if it doesn't jump, look what we have here. Revert if there isn't enough call data, right? So we have this push 0, which, okay, let me grab this. It's going to be this big thing here now. Boop, boop, boop. We're going to duplicate 1 for some reason. Looks like Solidity is doing, well, doesn't know that it already has these in here, and then it's going to go ahead revert. And this will be what's left on the stack, but it doesn't matter because the call is over because it reverted, right? So this code, we're going to jump to update horse number jump destination 3, but if there's not enough call data, it's going to revert. So this is actually one of the other cool things that Solidity does for us under the hood. Not only does it check for message.value up here at the top here, but it also checks for if there's even enough call data for us to continue execution. So let's go to jump destination number 3. And again, I kind of cheated. I already know where this one is. So I'm going to go directly to it. It's down here. It's actually right after this revert. So this is jump dest number 3. So what's this bit doing? Well, if we came from here, this is what we're going to be working with. So I'm going to copy this, paste this in here, and let's keep going. Okay. So next we have a pop. So it looks like we're getting rid of that 0 on the stack. Then we have a call data load again. So now what does call data load do again? It's going to I and then data I. So we're going to put the call data in here. And as I was filming, I forgot to take off this 0x04. So I'm going to take it off in a minute when I realize my mistake. And since the offset is going to be 4, it's going to ignore the function selector, just grab the data. The data we're going to get sent is like 0x01, 02, 03, 04, which is going to be the function selector, or wait, 1, 2, 3, 4. Yep. And then the rest of the data is going to be the actual data associated with this call. Remember, the call data looks like something like this. So we're starting from the 4th byte. We're starting from here, and we're loading this 32 bytes into memory. So call data of number to update. Cool. So it looks like we're finally pulling in the number to update into our stack. Now we're doing swap 2. Okay, this is another one we haven't looked at yet. Swap 2. A, B, and C, we're basically going to do C, B, A. So we're going to swap A with C. So we have call data, 04 call data size. So we're just going to do call data size, comma 0x4, call data number to update, comma the rest of this stuff. But we're going to do a swap one where what we're going to do is we're going to swap the first and second value. So now it's going to be 0x04, call data size, and then the rest of the stack. And we're going to pop. So it looks like for whatever reason, we just needed to pop off this 0x04. So why do we even put this on here? So if we scroll up, we have a jump test here. It looks like we pushed it on up here. Not sure why. Maybe it'll come in handy down here. I don't know. But we're popping back off that 0x04. So this is now what the stack looks like. And we're doing another jump. So essentially what this lump of code did is just grab the call data for updating the horse number and then delete some stuff in the stack. So it's kind of doing both of those. But the important thing is it's grabbing the call data for updating the horse number. And then we're going to jump to jump dest 4, which again, I've kind of cheated and I know is down here. So stay with me. This is right underneath the jump dest 1. So this is jump dest 4. And this is where we can finally run an store to save our value to storage. And we can only now do this now that we've done the function dispatch. We've checked for message.value. And we've checked the call data is long enough. And finally, we've received the number to use from the call data. So now that we're here, okay, let's go back to the bottom of jump test 3. And I know we're kind of all over the place now, but we're just going to copy this. And this is going to be our starting state here. So now we're going to do a push 0. So we're going to do the same thing, just push 0. Now we're finally going to do our store, which if we go here, store takes a key and a value. We're going to push to the 0th slot. What are we going to push? We're going to push the call data size. What's wrong? I just realized my mistake. I forgot. So when we call data load, we're supposed to take off the 0x04 as well as part of that opcode. So whoops, made a bit of an oopsie there. And so the call data size is what's actually getting popped off here. Cool. So now call data is at the top of the stack, or call data is at the top of the stack. Got it. So let's go back to jump dest 4. Great. And so it's not the call data size, it's the call data that's at the top. Okay, cool. Now when we do the store, it's these two. So at storage slot 0, we're going to store the number that we want to update. This is perfect. This is exactly what we want, right? And so store takes a key value, nothing else on the stack. So now our stack just looks like this. I don't know why we've pushed these, but maybe we'll find out in a second. And we have another jump. So we're going to be jumping to this spot here, and their stack is going to now look like this. And because we did that, our swaps are going to be a little bit different. This is now going to be up here. And it's going to be here. And it's going to be here instead of here. And so then when we jump, this is what's left. You can see as I'm kind of fumbling my way through this, I've even made some mistakes. So not this. And so we're going to jump to the, sorry. And so I need to delete all these 0x3fs that I accidentally kept in here. And you can see why this gets kind of difficult for you to keep in your head. But finally, we're going to jump to the 0x3 program counter. And all that's left in here is the function selector. So all these weird pushes that we did up here have basically panned out, right? This was a program counter to jump. This was a way to check for call data size. And then I forget what the 59 was for. Oh, and this was a program counter for this to jump to, right? So all these pushes end up being program counters for us to jump to. So we can say that. Set up jumping program counters in the stack. That's pretty clever of Solidity to have done all that. But so then we're finally going to jump to jump dest 5, which there's only one stop code here. So it's actually right here. This is going to be jump dest 5. And obviously we have a jump dest with our function selector, and then we end execution. So this is great. So we just actually went through the entire stack, the entire list of opcodes for update horse number, and there was a lot of stuff. So let's quickly do a recap of update horse number, all the different opcodes and all the different chunks of code that it set up for us. So once we do our function dispatch, right, way up at the top for set number of horses or update number of horses, it'll jump down to this first chunk of code here. And this first chunk of code is setting up all these different program counters and this call data size check. So this is going to be a program counter. This is going to be a program counter. This is going to be what's used to check the call data is big enough, and then a program counter. Then we go to jump dest 2, which is way down here. And this is where we actually do that check. We check to say, hey, is there enough data in the call data? Is there actually even a number here? Can we even, is there anything to S store? Is there enough data for us to S store something? Then we go to jump dest 3, which basically just grabs the call data for updating the horse number, deletes some stuff on the stack. And now we go to jump dest 4 with that number that we got from the call data. We store it on chain, we store it into storage, and then we jump to jump destination 5 where we stop and we're done. So great, we've just gone through all of the opcodes that are needed to update the number. Now you noticed in our Huff, we did a lot less, right? This is all we did. But we did a lot less because A, we did way fewer jumps. We just had everything in one block of code here. So if Solidity tries to get clever with its optimization. Number 2, we didn't do any checks for data size. We also didn't do any checks for message.value. So our Huff code was a lot simpler because it did a lot less, had a lot fewer jumps as well. But if we wanted to super optimize our Solidity, super optimize our binary, maybe we just chop off a whole bunch of those checks and we just do it like this. However, I will say checks are really good. We like checks. Checks help us secure ourselves from shooting ourselves in the foot. But now we know exactly what's going on in the hood, under the hood for that function. Let's keep going because there's a whole bunch more that we haven't done yet. So now let's go back to the function dispatcher and let's look for the read number of horses. So that's here, read number of horses. So what's kind of nice is right underneath this final jump dest stop is another jump dest, and this is going to be read number of horses, jump dest 1. And this is going to be the only jump dest for read number of horses, but there's going to be a lot. So we're actually going to go all of this is to return the read number of horses, which looks a little bit different than what we did in our Huff, right? This was all of our opcodes. We did a push here, sload, a push, mstore, push, return. So we've got a couple more things in here. We've got a swap, we've got a dupe, we've got an add. What the heck? We're doing so much more in here just to read the number of horses. Well, let's find out what's going on. So what's our starting state from the function dispatch? Well, it's just the function selector. Great. So let's do jump dest, function selector like this. Okay. And now we're going to push 0 for some reason. And then we're going to do a little sload. Okay, cool. So how does sload work again? So this is going to read from storage. You take a key and you return it with the value. So we're going to say at storage slot 0, it's going to be the num horses is now on the stack. Cool. So that seems simple enough. Now we're going to do a push 40. Okay. Interesting. Why are we doing a push 40? We didn't do a push 40 in our Huff, did we? No, we never did a push 40. Why are we doing a push? Well, I guess let's find out. Now we're doing an M load. Why are we doing an M load? Okay, so the offset. So this is going to read from memory. Okay, in bytes. Okay, so M load, it's going to read. Oh, and it's going to return the value. So this is finally where that free memory pointer is going to come into play. So way at the beginning of this call, that was the first thing we set up. We said, okay, at location, 0x40 is going to be 0x80, right? This is our memory way at the beginning of this. So now that we have this all set up, back down here, we're saying grab load whatever's in 0x40, and that's still 0x80. So remember, this is going to be our free memory pointer that we're now loading into memory. what we need to do in our Solidity here is Solidity needs to ask, hey, I want to store this variable in memory so I can return it, right? Because when we read number of horses, we need to store it in memory. Where is the free memory? I would like to store this value into memory. So now in our memory, we're saying, okay, at 0x80, there's free memory. And then here's what's on our stack. So now we're going to do a swap one. We're going to swap these two around. We're going to do a dupe 2. So we're going to dupe that 0x80, comma 0x80. And now we're going to do an mstore, right? So how does mstore work? Mstore offset value. So so we're going to duplicate the 2, put it at the front of this, because dupe 2 returns BAB. Yep, AB to BAB. So dupe 2 is now at the top. So now we're going to do an mstore, and at location 080, which is the free chunk of memory, we're going to stick the number of horses. So now what does mstore return? Nothing. So this is just going to be, these two are left on the stack. And now in memory, we're going to say at 0x80 is now going to be the num horses. So now 0x80 has stuff in it, right? Remember, what we just did was we just put the number of horses in this spot in memory. Storing the number of horses at 0x80 means now we need to update our free memory pointer to point to the next free section of memory. So we're going to do that. We're going to see 0x20 function selector, and we're going to add, so 0x20 plus 0x80. You can even do like a little cast to base 0x20, 0x80, 32 plus 128 is 160. So 160 going to be 0xa, yep, 0xa0. So now it's 0a0. The function selector, we're going to push 0x40, and now we're going to do mload, which is going to be the offset. So we're going to load what's at, oh, but I guess you'll notice Solidity is smart enough here to know that it's about to finish, so it doesn't end up calling an mstore ever again. So why are we loading from memory, right? So 0x40 is still going to be 0x80, right? Mload, just the offset, 0xa, and then the func selector. Then we're going to dupe 1 for, oops, now we're going to duplicate 1 for some reason. So this gets duplicated. We're going to swap 2. So this now goes to the top. We're going to subtract the 2. So we're going to say this minus 0x80, like that. We're going to swap 1 again. So now it's going to be 0x80, like that. And then we're going to return. Okay, so now I see why we're doing this all. So we actually don't end up updating our free memory pointer. Solidity is actually smart enough to know, hey, the call's about to end. I'm never using memory again. I don't even need to do that. But what we do need to do is return from memory those number of horses. So we kind of do a whole bunch of stuff here because at memory spot 0x80, we have the number of horses, and return, how does return work again? It takes the offset and the size. So we're saying at location 0x80 in memory, which again is the number of horses, return a value which is equal to this minus this. So this is what again? Deck 160 minus 128 is what? 32. So basically we're saying right here, return a value of size 32 bytes that's located at position 0x80 in memory, which we know is the number of horses. And then all we have left is the function selector. Good job, Solidity. Okay, and return ends the call stack. So is there any opcodes that we don't have annotated in here? Oh yes, there is a whole bunch of stuff, but I'll get to that in a minute. Is there anything above that we don't have annotated? No, we have everything annotated. We've gone through all of the contract creation code and all of the runtime code. This is insane. We just learned all of the opcodes Solidity takes for us to return a value from storage. Great job with this. And so you noticed it was a little bit more gas inefficient because in Huff, we didn't deal with a memory pointer at all. we said, hey, anytime we deal with memory, it's pretty much going to be free because this contract doesn't do a whole lot. Solidity doesn't know that. Solidity goes, oof, we always got to check the free memory pointer. Can I stick some stuff in memory? Luckily, to the Solidity developers' credit, they also coded in, hey, anticipate if the call is going to be done, because then you don't need to update the free memory pointer. That would be a waste of gas. So well done to the Solidity devs on that point. Cool. So we're all done with the runtime code. We're all done with the contract creation code. We just have this giant chunk of what the heck at the bottom here. So this is part 3, and this is the metadata of the code. So as you saw in all of our runtime code, never were we able to jump down here. So this is just inaccessible code that can never be reached by any transaction interacting with the smart contract, because all of this doesn't have a valid jump dest and nothing ever jumps down here. So these are some chunks of metadata that Solidity puts in to make it easier to identify what version, what optimization, how this was compiled, etc. And it's this metadata that often tools like Etherscan scan to actually do verification, to actually make sure a contract was compiled the right way, etc. It's not super important for what you're going to be working with, but if you want to learn more about metadata and how it's compiled and how it's built, feel free to jump into the Solidity compiler and check it out. Whew. Oh my goodness. But with this, you have just deconstructed a smart contract yourself. You have just gone opcode by opcode in a Solidity code base and figured out what it does. All of this. And you even know when you see FEs, you know what that stands for. So you know that this was the contract creation code. This was the runtime code. And this is the metadata. We went through the contract creation code, went through all the runtime code. We didn't really go through the metadata, but you know what it is. All this binary you just read and you understood. Now, you, just by doing this, can understand what this contract does, even if you've never seen the Solidity before. That's incredibly powerful. Now, before we get all done with going through opcode by opcode and EVM by EVM, I want to show you one more really cool thing. So we as humans can understand what opcodes do, right? And if you wanted to, you could probably even use your knowledge of opcodes now to reassemble or decompile this. Take these opcodes and actually turn it back into Solidity, right? You see this and you go, oh, okay, that's a free memory pointer. Okay, this is like a check for message.value. Okay, this is setting up some jumps, whatever. Here's our entry point. Okay, cool. You could reassemble this into Solidity. Well, guess what? There's also decompilers out there which try to help you decompile smart contracts. In the GitHub repo associated with this lesson, we can scroll down to some different decompilers that we can check out to try to decompile code. Yes, crazy. We can actually try to decompile code. Yes, crazy. There are tools that actually do exactly that or try to do exactly that. So we're on this DDoB tool here. And if we go to decompiler, we can either add a network address and it'll try to decompile, or we can add some hex bytecode. Well, for us, we can do that. Let's grab our runtime code and let's see if the DDoB decompiler is good enough to decompile this back into Solidity, right? So the Solidity for this is pretty simple, right? This is the entire Solidity. So we gave it the runtime code. Let's see if it can decompile it, and it'll take a few minutes. Let's see if we can decompile it back into Solidity. All right, let's see how it did. So it actually looks like it didn't do too bad here. So we have, okay, function selector, it's public payable, reverts. So, okay, that's pretty good. It's not exactly the Solidity we were looking for, but it's saying, hey, there's no fallback function. So cool. Okay, that's pretty good. Now it has function with this function selector, public payable. I think that's wrong. This is good. Require message.data.length -4 is greater than 32. Probably could have gotten rid of that as well. It recognized this was a uint 256. I mean, it could have been a bytes 32 either, but okay, cool. So it looks like this was indeed our set number of horses, right? So it's saying storage position 0 is set to the var argument. That's great. So a little weird, not quite right, but yeah, it essentially got it. And this, it also got, right? This is the function selector of read the number and return storage variable 0. Great. And then finally, we have this, where I'm not exactly sure what it's doing, but I think this is it trying to the function dispatcher, which it got a little confused about. So actually, it did pretty good, right? I mean, our contract was pretty simple, but it did a pretty good job here. But as you can see, decompiling assembly code is tough. It's not easy. So, but a really cool tool nonetheless, and I expect it to get better and better as AI gets better and better. Heimdall-RS is another decompiler that you can use as well, which does some really cool stuff. Or disassembly, or however you want to call it. But anyways, okay, we've learned a lot. So let's go over everything we learned in this Sulk breakdown one more time, and then we'll never walk opcode by opcode again, unless we have to, unless we want to do some crazy optimization, unless we're auditing a compiler. There's a ton of reasons why we might want to look at opcodes, but for this course, this is going to be it. If you want to get better at these opcodes, if you want to learn them more, definitely check out EVM.codes. It's a phenomenal website which shows you all about the different opcodes. And I highly recommend, if you want to go super crazy mode, you get crazy good at Huff, or maybe you build your own smart contracts in opcodes, whatever you want to do. If you do not feel comfortable in these yet, the more you play with them, the more you use them, the better you will be. But in this, we learned, okay, most smart contracts are compiled into 3 sections: contract creation, runtime, and metadata. This is how most compilers set them up. You can, of course, have a compiler which splits them into as many sections or as few sections as you want, but this is how most of them do it. Huff really just does contract creation and then runtime code. In Solidity, pretty much all code starts with setting up a free memory pointer. We didn't really have to update it too much in this code base because we weren't working with memory a whole lot, but we can see where if we had a lot of memory variables, we would need to consistently update the free memory pointer so that we always knew where memory was free. And this is one of the first things Solidity always does, no matter what. We learned that Solidity at the opcode level has a ton of checks. We check for message.value. We check often for call data being long enough, etc. And we learned in the contract creation code, we basically do this code copy opcode and copy paste all of our code on chain. We learned the runtime code is going to be the entry point for every smart contract. It's going to be very similar to the main function of our Huff code, pretty much exactly the same actually. We learned Solidity does a lot of checks and jumps all over the place with all these checks, checking for call data, message.value, etc. Once it's done a whole bunch of these checks, it enters its function dispatching, where it compares function selectors with the first 4 bytes of the call data given to it by the transaction. We learned it has a bunch of jump destinations to revert. We learned it sets up a whole bunch of jumps, often in its own little chunk there. And we learned about some of the different opcodes and working with the free memory pointer, etc. We literally went opcode by opcode, and we basically manually disassembled or understood what each one of these opcodes is doing. So if you followed along so far, amazing job coming along with this. Please be sure to tinker with stuff like, oh, what if I change this to equals 7? How does that change the opcode? Oh, what if I added another variable here? UN256 AAA equals 1 or 7. UN256 BB equals 99. How will the free memory pointer be updated if we have those? Please, please, please be sure to tinker with this until your curiosity is satisfied. But whew, okay, we've learned a ton here. Just by doing this, you pretty much are now an opcode savant. Like that's kind of it. There's not that much more to think about when it comes to working with EVM, Solidity, and smart contracts. Except the way mapping and arrays work, it's kind of tricky. Yeah. On a very high level, really, you've learned everything you need to know, right? Every other combination of opcodes is something you can figure out. You know, even things that might seem complicated, like fallback functions or precompiles, etc. All those opcodes are something you can figure out. You can go to evm.codes and work with them. The only tricky thing here that we haven't gone over is going to be precompiles. So let me quickly explain precompiles. So precompiles are addresses in the EVM world that do very specific things. So address 0x0 is going to be the EC recover precompile. So precompiles are basically special contracts that are bundled with the EVM at very specific fixed addresses. They're called from the opcodes just like regular contracts with instructions like call, and there's a gas cost mentioned just purely with the cost of the contract. So basically, if you're working with an EVM chain, there's going to be very specific precompiles which have inputs and outputs, very specific contracts that allow you to do specific things, right? On each fork, there's often a different precompile, a new one, or remove one. So these aren't opcodes per se, but they are things that you want to keep in mind when you're reading opcode by opcode. And if you're going to decompile a smart contract and you see some hard-coded addresses, maybe they're working with a precompile. And if you see a static call to like a weird one address that's in when you're decompiling or when you're reading opcodes, that's probably a precompile that they are calling. In the security course, we talked a little bit about signature replays, and we talked about some of these precompiled contracts like EC recover, SHA-256, etc. So now we're not going to go through this again, like I said, but if you want, I have the Huff breakdown on the GitHub repo associated with this course. But this was cool. We have horsestore.sol, we have horsestore.huff. So we've learned a couple of different ways we can actually do low-level programming in Solidity. We can do pure binary or opcodes. We can do a low-level language like Huff. We can also do this programming language called Yule. And what makes Yule really special is that it's actually built into Solidity, and you can actually do inline Yule or inline assembly right in your Solidity code. Doing so achieves several goals. We can actually write our high-level Solidity, but for specific parts where we need very specific fine-grained access or we need them to be highly performant, we can actually just write them in Solidity. We can actually just write them in assembly. If we scroll down in the Yule documentation, we can see, if we scroll all the way down, a list of the different commands for the EVM dialect. And this is the list of commands that you can use in Yule or assembly. And it's going to look really similar to what we just did with Huff, right? There's a lot of familiar opcodes in here. We have stop, add, sub, mul. Let's keep going. Equals, is zero, and, or, right shift, left shift, add mod, mul mod, cacac256. All of these different opcodes we can use in Yule. And we can do this, like I said, to make more gas efficient smart contracts or just have more fine-grained control over our smart contracts. So let's actually rewrite our horsestore.sol into horsestore.yule.sol. So what we can do, we're going to create a new file, horsestore.yule.sol, and we're just going to paste our horsestore code in here. And we're just going to make this pretty minimal, but we're just going to replace the code inside of update horse number and read number of horses with some assembly or some Yule. So when working with Yule in your Solidity, you just put assembly and these little brackets and boom, now we have access to Yule. And simply enough, if we want to do this line in assembly, all this is doing is what? It's basically just an S store, right? We're storing new number of horses into the slot of number of horses. So we can actually just do that right in assembly by saying S store number of horses dot slot, comma new number of horses. So this is some cool syntax you can do in Yule. You can do this little dot slot, which will get you slot number 0. Now down here, for reading number of horses, we can do the same thing, but instead we're going to do what? We're going to do an S load. So we can say let, this is how you create a variable in assembly. We'll say num set. So this is how you set a variable in assembly. So num is going to be set to S load number of horses dot slot. So once again, we're calling the S load opcode, and we can go back to evm.codes to once again see how that works. S load takes a key, returns a value, boom, just like that. And then we're going to do mstore 0 num. So we're going to store. So same thing. We're going to do the mstore opcode, offset value, offset of 0, value of num, And then we're going to return 0, 0x20. Return 0, 0x20. So as you can see, Yule is a little bit different than working with Huff or working directly on the stack. When I called mstore in Huff, I'm expecting these to already be on the stack. In Yule, you almost add them as parameters to the opcode. So mstore says, okay, I need the offset to be at the top of the stack, and right underneath that is the value. In Yule, you just do it like this. So what Yule does is, okay, I'm going to push the number onto the stack first, then I'm going to push 0, and then we're going to do mstore. So it almost abstracts away the stack a little bit for you and turns these opcodes into functions themselves. And how do we test this? Well, you already know how we test this. If we go into our horse store sulk.t.sol, we copy, paste it, we'll create a new test called horse store Yule t.sol. In here, we're going to do the same thing as what we did in Huff. We're going to say function set up, public override. We're going to override it. And we're going to say horse store equals, and let's import horse store Yule from src / horse store Yule.sol. Do we have horse store Yule? Horse store, yep, horse store Yule. So we'll name it horse store Yule in here. Horse store Yule from horse store Yule. So horse store is going to be new horse store Yule, but this obviously won't. Oh, src horse store Yule.sol horse store Yule.sol. Spelling is hard. Great. And it's going to give us an error here saying, hey, you can't actually do that. So this is where we're going to go ahead, make a new iHorseStore.sol. And we're just going to grab these two functions. We're going to do a pragma. We're just going to do an interface to get this to work. GPL 3.0 only, 0.8.20 interface. iHorseStore. Oh, ChatGPT. Thank you. So now in our V1, we're going to import iHorseStore from like that. It's going to be an iHorseStore. We're going to wrap this in wrap this in iHorseStore. We're going to wrap this in iHorseStore. Address horse store like that. We're going to do the same thing for this. Instead of importing horse store, we're going to import iHorseStore. Sulk, that's fine. For the Yule, we're finally getting there. iHorseStore, comma, iHorseStore. Nice. Okay, and if we did all that right, we should be able to run forge test. I know that was kind of a really quick way, but I basically just created this iHorseStore interface and then wrapped all of our contracts in iHorseStore. All the tests should run exactly the same. They're all being tested on the same interface. And we do indeed see, even with some fuzzing, our Yule smart contracts performed exactly the same. They passed the exact same tests as our Solidity and our Huff. So congrats. You've just written your first little bit of Solidity, and then you've run a differential test for your Yule against it. Now, we're not going to spend a ton of time going through Yule and teaching you Yule because you've kind of learned it already. Just by knowing opcodes, you've essentially learned how Yule works. Most of Yule works really similar to any other programming language, with the biggest thing being kind of down here in this EVM dialect, where these are kind of the most important pieces, these opcodes that are kind of turned into functions. But since you know Solidity, you can always come back to the docs and write some really clever assembly because you kind of now have access to the different opcodes. Coding in raw Yule, pretty much nobody does. And in my opinion, nobody should do this for production unless you want to just be super sick at assembly or Yule for some reason. I don't recommend coding in Yule. And so for this section, this lesson, I'm going to tell you right now, this is 100% optional for you to do. If it's up to me, I would rather you get super good at Huff, because Yule abstracts a lot of stuff away. Huff abstracts just enough that it's easier to use, but you don't lose the feel of working with assembly. working with Yule, it almost feels like you're kind of fighting with the EVM, the assembly a little bit. That's just my opinion. So this is going to be 100% optional. Take it as you please. So we're not going to build any crazy assembly things here, but we are going to go one step further because you can do inline assembly, and that's how most people use Yule, but you can also do standalone Yule. Now, Foundry doesn't love standalone Yule. It doesn't love those being in the SRC. So we're going to make our own file here called Yule. We're going to write the entire horse store contract in Yule, and this will give you some great Yule practice. Are you ready? All right, good. Horse store Yule dot Yule. So let's go ahead. Let's rewrite our horse store into completely 100% Yule. So instead of the keyword contract in Yule, the keyword to create a contract is actually going to be object. So we're going to say object horse store Yule like this. And same as Huff, when this object gets deployed, it's going to deploy whatever's inside of our code. So there's another kind of class in here called code. And to get some syntax highlights for our Yule code, I've actually installed this Solidity plus Yule VS Code extension, which is going to give our syntax here some really nice highlights. So that's what I'm using for syntax highlighting here. So in here, actually really similar to Huff, we have to set up our contract deployment. So unlike our .huff code, our Huff code automatically gives us the contract deployment. Unlike that, we actually have to write our contract deployment in Yule ourselves. So the way that we do that is we say data copy 0, data offset. This all makes sense in a second. Runtime, data size, runtime, and then return 0, data size, runtime, like this. This data copy is a bit of a special Yule word. So you'll see there's not quite a data copy function in the opcodes. We have call data copy and then return data copy. So these three functions, data size, data offset, and data copy, are a bit specific to Yule, and they're used to access other parts of a Yule object. The data copy is equivalent to code copy. So this data copy is basically just code copy. And if we look at code copy, it takes destination offset, and then the size. So we're going to stick this in the 0th slot in memory. We're going to start at the runtime object in our Yule, which we haven't created yet. And we're going to copy it for the iteration of the runtime, and then we're going to return it. So obviously, next we're going to have this object runtime, and we're going to add some stuff into it. But now that we have this, what this data copy is going to, just one more time, this data copy is code copy, and it's going to say, go into our code here, grab the object that starts with runtime, which is down here, and grab it up to the size of the object runtime. So it's basically saying grab the whole runtime and stick it into the 0th slot in memory. And then return works just like the return opcode. So it's saying starting from the 0th slot of memory, return all the data associated with the data size. So this is how we actually stick the runtime code on chain. Now compiling straight Yule is a little bit tricky. You do need access to the sulk binary. So you sulk -- version. There's a whole bunch of different ways to install this. So this will be install sulk or installing the Solidity compiler. You can come to the documentation to install it if you want to come here. The way that I like to have it installed, is actually with this tool sulk select, because this will help you switch between different Solidity versions depending on what you're working with. So go ahead and install sulk however you feel, because you'll need it for this. Sulk -- version. Great. Once you have sulk installed, the way we compile Yule is we're going to do sulk -- strict assembly. We can do -- optimize, optimize runs, whatever you want to do, 2000, and then /Yule /horsestore.yule.yule. Oops, and actually, excuse me, we need the keyword code in here, which code, boom. Let's do that, recompile, -- bin for binary. And you'll get kind of a ridiculous output that looks like this. So I usually like to pipe it into grep 60. to find the line that just has the binary, and that's what this is. So this will be your UL compiled into binary. Great. So this is what we're going to use to make sure our UL actually is compiling correctly. So this is our contract creation code. Now we can create our contract runtime code inside of this. So the first thing we're going to want to do is create a function dispatcher, just like Huff, just like we saw in the bytecode. And to do that, we're going to do this switch selector, like so. So this is going to be a switch statement, which we haven't really seen in Solidity. But basically what it says is, okay, we're going to look for the function selector. And this selector actually isn't a keyword. It's going to be a function that we're going to define in a little bit that will grab the function selector from the call data. So it's saying we're grabbing the selector from the call data, and we're going to do a switch statement. So we're going to have a couple of cases of, hey, what to do in case of X, what to do in case of Y, et cetera, et cetera. So for the update horse number, UN256, horse number, the selector is going to be 0x. Actually, I'm going to copy paste it. It's going to be this one. So we would say if the function selector is this, so we'd say case this function selector, do some stuff. And we're going to define that in a second. If it's, and I'm going to copy paste this, which is the read number of horses. If it's this, so this case basically means if the selector is this, do something else. And then if neither of those hit, the default is going to be to revert. Let's put a little comment down here, decoding functions. And this is where we're going to put some helper functions. So we're going to say function selector returns S. And so S is going to be some variable. This is how we do returns in UL. And we're going to say S is going to be set to divide call data load of 0. So we're going to load all the call data by this giant number. And if you don't want to write this out, you can copy paste it from the GitHub associated with this course. UL is a little bit weird. So which is why we're kind of speeding through this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40, 1, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 5, 6, 7. And this is how UL recommends you get the function selectors. So similar to like a named return, we don't actually have to return anything here. It just automatically knows to return it as such. Return the S variable. Seems super odd, I know, but this is what we're doing. So we're going to divide the call data loaded by this, and doing so, we surprisingly get the function selector. Cool. So cool. So we have the selector. What do we do in the case it's update? What do we do in the case it's read? Well, let's start with update horse number first. So if we want to update the horse number first, we're actually going to create a new function called store number. And as input parameters, we're going to actually input decode as uint 0, which is going to be another little helper functions down here. So we're going to create this function decode as input offset. So we're setting the offset just automatically to 0 in there. And we're going to return some value. We're going to let position equals add 4 to the mole of offset 0x20. I know this probably doesn't make any sense here, but basically what this is doing is we're getting the offset, multiplying it by 20 by 32 bytes and adding 4. So we're saying what position in the call data. So this should be function, and this will be position in call data that we're going to pull from. So we're going to add 4, which is the function selector, to whatever the offset is. Once we have that position in the call data, we can say if the call data size is less than the position times 32 bytes, then we should just revert, right? And this is equivalent to us doing that size check. So we're saying if the call data size is less than the position plus 20 we should revert. So if there's only one piece of call data, it's just going to be 4 plus 20, 24. So the call data should be at least a function selector plus 32 bytes. But anyways, so once we have all that, we can now do v equals call data load position in the call data. So we're loading the position in the call data. That is hopefully going to be the value that we're updating. So we have the store number as an input. We're grabbing the data from the call data for this store number function that we're going to create now. So now below the default revert, we're going to create that function store number, new number. And since it's already been decoded from our call data, we can actually just do an store 0 new number. New number. If we had a lot of memory variables, maybe we're doing something with a free memory pointer. We're not, so we can skip that. And then finally, if we want to read the number of horses, we're going to return uint read number like this. And so we have these two functions to define. Let's first define function read number, which is going to return a stored number. We're going to say stored number is set to sload 0. So we're just grabbing whatever is at the 0th position. And then we're going to use one of our helper functions at the bottom here. We're going to say function return uint v mstore 0, v, and then return 0, 0x20. So this just helps us return it to us. So how would we test this? Well, what we would do is we would run the compiler, POS not found. Oh, position column data. All right, well, let's make sure it actually compiles first. And then we would take this, look for the invalid opcode for the 39. I believe that that's what we're looking for. Yep, that's the code copy. What is it, 3F? Where's the invalid opcode? FE. FE is right here. Then we would take all the code after the contract creation. In one of our tests, what we would do is we would say bytes Yule code equals B like this, something like this. And then we would deploy it directly from bytes. I don't want to do that, so I'm going to skip that. However, if you want to go ahead and deploy the Yule code that you compiled and test it, do an equivalence test, do some differential fuzzing, you're more than welcome to do so. And I highly recommend you to do so because you'll learn a lot and it'll be a ton of fun and you'll feel like a badass. So if you want to go ahead and do your differential testing with the Yule code, pause the video right now and have fun. So that's our whole Yule smart contract here. A little confusing, I know, but let's do a quick rundown of what we did, what we built here. So for our Yule, all Yules start with some type of object with code inside of it. Most of the time, the code section is going to be your contract deployment. And then you'll have another object, which will be your runtime, and you can call it, whatever you want to call it. Inside of our runtime code, the first thing we do is set up our function dispatcher for our two function selectors. If we want to store a number, then what we're going to do is we're actually going to decode as uint. We're going to basically take the call data and get the value that we want to store into storage from the call data, and then simply do an store to do so. If we want to read the number of horses, we're going to first actually read the number from storage, which is just a minimal sload. And then we're going to return it as a uint, which is just doing it a little mstore and then a return. And then if neither of those function selectors are hit, we're going to revert. Okay, so now we're feeling really good about ourselves. What have we just done? Well, we've written a minimal contract in Solidity. We then took that Solidity and we said, I'm going to rewrite it in Huff, which is essentially us writing it in opcodes. Then we took the Solidity code and we literally went opcode by opcode, teaching us how Solidity actually gets compiled and how these assembly opcodes work at the lowest level. We even looked at a decompiler real quick, which shows us more about how opcodes work. We learned a little bit about the free memory pointer, and we learned about the stack, the memory, storage, etc., and all these little components of the EVM that are important for us to understand the opcodes. we learned about precompiles. We learned about that, oddly enough, there's some precompiled contracts that are deployed on these different chains for doing different bits of math. We wrote some equivalence tests or differential tests for both the Huff, the Solidity, and our inline Solidity. We wrote some inline assembly in our Solidity, and some of us even wrote the entire horse store smart contract in Yule, which is kind of crazy. And now we're going to kick it up a notch. So we're going to make a slightly more advanced smart contract. So we're going to make this horse store v2, src horse store v2. And this is what this looks like in Solidity. And I'm actually just going to copy paste it into our code base because we're not going to write the Solidity. So I'm going to make a new folder, horse store v2, new file, horse store.sol, paste it in here, boom. And because we're using some OpenZeppelin smart contracts, we're actually going to go ahead and install those as well. So that's going to be forge install OpenZeppelin / OpenZeppelin contracts. We're going to install a very specific version at v 5.0.1 -- no -commit open contracts. Needed an S in there. And while that's installing, we're going to go to foundry.toml. We're going to add a little at OpenZeppelin / equals lib / OpenZeppelin - contracts / forge build to make sure it builds. Looks like I messed up. Oops, this is going to be a horse store. And once we do that, we're also going to grab this iHorseStore.sol, which is a slightly different implementation. iHorseStore.sol, paste it in here. Let's see if I did everything right. Forge build. Okay, cool. Looks like it did. So I know I did a whole bunch of stuff there, but let me just tell you really quickly what your starting point is. So you're going to have HorseStore.sol all set up for you. And then you're also going to have this iHorseStore.sol. And this is going to be our v2, which is a little bit more intense. So we're importing ERC 721s, and our horse store has a mapping, and it has some constants, and it has a whole bunch of stuff in here. So most importantly, all this contract really does is it allows people to mint horses, feed your horse, which just updates a mapping to be the block.timestamp. And then there's a function called isHappyHorse, where if given a horse ID, it returns true if the horse was fed within the last 24 hours. And the reason I want to do this is because we're going to learn about some more advanced huffing. And most importantly, we're going to learn how at a low level, this mapping stuff works. I know a lot of you already know, but we're going to write the Huff to rewrite this smart contract. And we can go one step further. So what I want you to do is copy paste this base test v2.sol, which has most of the tests for you already. So let's create a new folder, call it v2, create a new file, base test v2.t.sol, paste the whole thing in here. Then I want you to copy paste the horse store Solidity. So we're going to do horse store v2 test, horse store v2 solidity test.t.sol, horse store of solidity v2, and then also copy paste the Huff. So pretty much I want you to copy paste everything except the actual Huff. So horse store v2 Huff test.t.sol, paste it in here. And we're going to create in the v2 folder that we just created .huff, which will be blank. So I know the answer key obviously is in here, right? If we go to horse store v2, the answer key is right here. But this is what I want us to do. If we run our test now, forge test, everything should pass except for the Huff tests. Everything should pass except for the Huff tests. So let's see. Sure enough, all the Huff tests fail. So what we're going to do now, and you can even pause the video and try to do this yourself, is we're going to write the Huff code for this horse store v2. And it's a little bit more intense because, first off, it's an ERC 721. It's got a mapping, it's got several mappings, and there's a whole lot for us to do. So if you want to pause the video, rewrite this in Huff yourself, I highly recommend you to do so. Otherwise, we're going to do this together, and this is going to be how we're going to wrap up the section. We're going to get some more assembly, some more low-level EVM practice by rewriting this smart contract in Huff and making sure it passes all of our tests. You can see all the tests in here, and I recommend you going through them if you want to get a good idea of what we're even testing for. So we're going to finish up this section by writing horse store v2.huff, getting it to pass all of our tests, and then we're going to be done with the section. And you, my friend, you will have learned so much about opcodes, low-level EVM, low-level assembly, that I will be more than happy to send you on your way and start analyzing bytecode. You will have the power to go to a smart contract that has not been verified in Etherscan and say, you know what? I could figure out what this is doing. And that's incredibly powerful. So let's buckle up and let's rewrite horse store v2 in Huff. All right, so now that we've been through this once before, you already know how to get started. Let's go ahead and get started with our define main, or our macro main. Takes 0 and returns. Now this takes and returns is going to be what it takes off the stack and what it returns on the stack. Kind of just like any of the opcodes, right? Any of our opcodes, they take something off the stack and put something back on the stack. So if we wanted to do that, we could do that here. And in this main function, we're going to do pretty much the exact same thing as we did in our v1. So I'm actually even going to just copy paste like so. Boom. First, we're going to grab the call data and give it a little right shift so we can get the function selectors. And now we're going to do a little bit of function selecting dispatching. So let's go to our horse store v2. Let's get the functions that we need. Okay, we need a mint horse function selector. What else do we need? Okay, we need a feed horse function selector. Okay, cool. What else? Okay, we need an is happy horse function selector. And is there anything else we need? Okay, we have a public variable, horse ID to feed timestamp. So whenever you have a public variable in Solidity, this is actually turned into a getter function. So yeah, we actually need that one as well. So we're going to need a horse store, horse ID to feed timestamp like that. Do we have any other public variables? Oh, horse happy if fed. That's a public variable. So we need a getter function for that. And that looks pretty good. So same thing. We know how to do this. We're going to have the function selector up here. We're going to do dupe1 __ func sig. And this is where we put the mint horse function sig, but we know we could do like cast, blah, 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 get the function sig, but we know we can actually just define a little horse store interface at the top to make this a little bit easier. So we're going to define, what is it? Mint horse, non-payable, returns nothing. Define, was it feed horse? Oh, look at that. Oh, define function, excuse me. Function. ChatGPT is already helping me out. Feed horse, not a horse ID, a uint 256. Non-payable returns nothing. Great. What else? Define function is happy horse, uint 256. View, perfect, returns bool. Define function. What else do we need? Horse ID to fed timestamp. That looks good. Define function. Oops. Define function. Thank you very much. And cool. So now what we can do, we can just grab those function signatures right from our interface here. Feed horse equals feed horse jump if. Right. This is going to be the same setup as what we did here. Dupe1 func sig equals our jump destination and then jump if. Since we made a jump destination down here, oops, down here, we would say feed horse, and we're going to create a macro called feed horse that we'll define later, and I'll update all these in a bit. So we're going to do the same thing. Dupe1. Oh, ChatGPT has got me. Thanks, ChatGPT. Oh, actually, we should do mint horse first. Dupe1 func sig mint horse, mint feed is happy, horse to ID t. This is a great reason for using ChatGPT, by the way. Pretty much just gave me all the answers right there. And those look pretty good. Let's see if it's good enough to do this stuff down here. Okay, it looks like it's a little less smart. So feed horse we got. What else we need? We need mint horse. What else? Is happy horse. That. I'm gonna do this horse happy fed within. I like having my jumps lowercase. Horse happy fed within. And those look pretty good. And boom, look at how much quicker this was for us to write now that we actually know how these work, right? We have our main, we do our function dispatching, and ChatGPT, for me, pretty much did most of the writing for me. So cool. So let's get started writing some of these functions here. And then we'll worry about constructors and variables and all that stuff in a little bit. Let's do the feed horse first, actually. Yeah, let's do the feed horse first. Above here, we're gonna do define macro feed horse takes 0, returns 0, because we're not gonna worry about anything on the stack here. And let's actually look at the code and see what this does. Okay, so we have this mapping horse ID to fed timestamp, and this is probably the most important function we're gonna have to do for our learning, because we're gonna learn about the mappings, timestamps, all this good stuff. So we're gonna need to get a block.timestamp. Is there an opcode for working with timestamps? Let's do timestamp. There sure is. It's just called timestamp. It sticks the timestamp onto the stack. So let's go ahead, we'll just do timestamp, and this should mean that on our stack now is the timestamp. Okay. What's next? They're going to send us some call data. They're going to do 0x. And then they're also going to send us what are they going to send us? Horse ID to fed. So, right, it looks like when you feed the horse, it just updates the last time it's been fed. So, and then it's going to give us a uint 256 in the call data. So we know how to get this. So first we're going to do 0x04, and then we're going to do call data load. So this will give us the horse ID and the timestamp. Why? Because when we call data load, we're saying, give us all the call data after the first 4 bytes, which is going to be the function selector. Boom. So we're just going to get the uint 256 here. Next, well, what do we need to do? Well, we have the timestamp. We have the horse ID. So now we need to do what? We need to store the timestamp with the horse ID key. So how do we do this? Well, if we look at the Solidity documentation, and we've definitely learned this before, mappings actually work with a very specific algorithm. The value corresponding to a mapping key K is located at kcac 256 h of k.p, where dot is a concatenation and h is a function that is applied to the key depending on its type. And then there's a whole bunch of math in here. I've gone over this before in the Foundry full course, so I'm not going to go over it again here. But basically, there's some algorithm that we need to use here. Now, I personally don't want to have to write this algorithm out every single time I use it. And guess what? A lot of people thought the same thing when working with Huff. So there's this tool called HuffMate that we can actually use that actually has a lot of these built in. If we go to SRC, we go to tokens, it has an ERC 721 that we're going to use, but additionally, it has utils, data structures, hashmaps.huff. And this is how hash maps or hashing or that algorithm for mappings look like and are used in Huff. And yeah, this looks pretty terrifying, but these are the opcodes that Solidity uses under the hood when it works with mappings or hash maps. And hash maps are pretty complicated. So what we can do is we can install HuffMate and take use of these contracts in here. So I'm going to copy this, forge install huff language / HuffMate, forge install, --no -commit, like this. And now in our Huff, we can actually import the hashmap library by doing a Huff import. So we can say #include lib / huffmate / src / data structures / hashmap.huff. And now we have access to this hashmap thing. So now if we open up the hashmap.huff, this is going to make it a lot easier to work with slots, have those algorithms, and we don't have to really think about the algorithms anymore, which is really nice. But for any variable in storage, even if it's a mapping, it still needs some type of storage slot. Hey, we're going to base this algorithm around a storage slot. So what we're going to do is we're going to make a constant. Define constant horse fed timestamp location equals free storage pointer. So this is going to be the storage slot for the mapping. Obviously, the whole mapping is not going to fit into this. The elements are going to follow that hashing algorithm to find their own storage slots, but the mapping needs kind of like placeholder to do the calculation for. So now that we have that, we can access its value like this. And now our stack is going to be like this. And now that we have the location, the horse ID, and the timestamp, if we go back to our Solidity, we're saying, okay, at mapping horse ID fed to timestamp, and the horse ID fed to timestamp mapping storage slot is going to be this location here. Update it at index horse ID, or algorithm horse ID with this timestamp. We can do all of that with a macro called store element from keys in this hashmap.huff. So what this store element from keys does, it's another Huff macro. And unlike all the macros we've done, it actually pops 3 things off the stack and returns nothing, right? So it pops these 3 things off the stack, returns nothing. Don't worry about the memory pointer for now, or at all, really, for the portion of this course. But basically, we're gonna call this function get slot from key, get slot from keys, and this is the code that actually says, okay, based off the slot and the key, I'm going to do some hashing to return the slot that this data should go in. So this is the Huff that's responsible for getting us the correct slot with all the hashing and stuff. Once we get the correct slot, we just call store, right? That's it. So we can actually just call that store element from keys, We're just going to pass 0x00 as the memory pointer. That's the free memory pointer. So it's basically, we're passing in, hey, where's their free memory? For us, we're not going to really care about free memory too much at all. So we're just pretty much always going to pass in 0x0. And then now we're going to have nothing, and it's that easy. So we kind of cheated. We kind of made it a little easier using this hashmap.huff. But if you're like, whoa, what the heck just happened? I highly recommend pausing the video, going through this macro, store element from key, and seeing how this get slot from keys function actually calculates the storage slot of a hash map. Because this is exactly what Solidity is doing on the back end underneath the hood whenever we do a mapping like this. And cool. And that's it. And that's our feed horse macro. Great job. All right, next, let's do this one. Horse ID to fed timestamp. I'm going to change this to get horse fed timestamp. So what this is it's simply the public getter function for getting last fed timestamp based on a horse ID. So that's pretty simple. We've done stuff like this before. Let's go ahead and create this macro. Define macro, get horse fed timestamp. It's going to take 0. It's going to return 0. And what is this one going to look like? Well, we're going to need the horse ID from the call data. So we know how to do that. 0x04, call data load. And it looks like Copilot's already helping me out here. Horse ID. This is how we get the horse ID from the call data. That makes sense. Then this is the mapping for the horse fed timestamp. So we're going to have that now in the horse ID. And we're going to need to do, instead of store element from keys, we're going to need to load an element from keys. So this is where we kind of do the reverse of what we did for store. So this used that hashing algorithm to store an element. Now we want to load an element. Let's say if there's a macro for this, load element from keys. There sure is. And this does the exact same thing, get slot from keys, but performs an S load as opposed to an S store. So we can do the exact same thing here. So we're going to do load element from keys, free memory pointer of 0x00. And this does what? Takes 2, returns 1, load an element onto the stack from the 2 keys. So what's going to be left on the stack is going to be the horse fed timestamp. Ta-da. Now that we have that on the stack, we're going to need to pop this into memory. So we're going to do 0x00 and then m store, which does what? It's going to empty our stack. And now memory is going to have at 0x0, it's going to have the horse fed timestamp. And then we need to return. So we're going to say 0x20, 0x00, return. And you'll see that syntax a lot. This says we're going to take 20 bytes starting from the 0th position in memory and return that. So basically we're going to return the horse fed timestamp and we should be good. All right, what's next? Is happy horse. This one is going to be one of the most complicated ones because if we go to the horse store, there's a whole bunch of conditionals in here. So what we got to do, we're going to need to get the timestamp when the horse was fed. We're going to need to compare it to the current block.timestamp minus this horse happy if fed within. And if it's too small, return false. The horse is not happy. Otherwise, return true. So this one's going to be a little bit more complicated and it's going to be even more fun to make. So let's do this. Define macro is happy horse equals takes 0 off the stack, returns 0 onto the stack. So what's the first thing that we need? Well, we're going to need this horse ID from the call data. We know how to do that. 0x04, call data load. And that looks like what? Boom, boom. Horse ID. Nice. Then what do we need to do? Well, we kind of need to do exactly what we did here, right? We need the horse fed timestamp. So I'm actually going to copy this, paste it here, and ta-da. Now we have the horse fed timestamp. Cool. We could have turned this macro into like takes 2, returns 1, where it takes off the stack and returns from the stack. And then we could have just called this macro. I didn't want to do that. So cool, moving on. So we have the horse timestamp. Great. Now we need the actual timestamp. Okay, we can do that. Timestamp. Ta-da. Now we have both of those on the stack. Now we're going to need to be a little bit clever here. We need to do some comparisons here. And I'm just going to do 2 dupe 2s. And I'm going to tell you to trust me, it'll be good. It'll be good for us. So timestamp, horse fed, timestamp, timestamp, horse fed, timestamp. Yeah, just trust me that the 2 dupe 2s are gonna work out here. So what we want to do is we want to subtract horse fed timestamp from the current timestamp. So this actually isn't exactly what we're doing here, but it's going to return, but it's going to end up returning the same result. So we're going to do sub here, and we're going to say, let's take the current timestamp, subtract it from the previous timestamp, like that. And now that we have this, we're going to need to compare that to this horse happy if fed within constant, which we have not defined yet, but we should. So up at the top, we're going to need to define that. Define constant horse happy if fed within const equals, and this is not going to be a free memory pointer. This is going to be a legitimate true constant. And here we have 1 days. Let's pull up chisel, see what 1 days is. 1 days. This is the hex for 1 days that we're going to copy, and we're going to paste it up here. So cool. So this is basically saying if the horse hasn't been fed within a day, it's not going to be happy. And this is the constant that we can use. So we want this constant on our stack because we're going to have to compare it. So back in our is happy horse, let's grab that constant, and it looks like I should move these all up by 1 at least. And now on here, on our stack, we have horse happy if fed within const, the subtraction, and then those 2 other variables. Now what we can do, a comparison. So we can go back to EVM.opcodes and look for a greater than or equals to. So there's greater than, sign greater than. There's no greater than or equal to. So we'll have to do a greater than and then an equal to as well. So in here, we'll say greater than. We want to check if this is greater than this. So we'll do greater than. And if we're checking greater than, we're saying basically horse has been fed within 1 day, a true false, like that. And then what we can do is we can say, okay, well, if this is true, let's go ahead and jump. So we can create a jump destination by doing start return true, jump if. And I'm going to make a little jump destination down here, and we'll do some stuff with that in a bit. So jump destination, jump if, and that means that now we're just going to have a timestamp and horse fed timestamp. But we're not done because we checked if greater than, but this is greater than or equal to. So now we also got to check for equal to. So this is why we did these double dupes at the beginning, because now we can just run the equal opcode to see if they're equal. I'm going to do something a little bit cheeky here and just follow me for a second. When we do this start return true jump if the horse has been fed within 1 day, but not at exactly 1 day, we're going to jump down to here, right? And when we jump down to here, we're going to run this opcode of x01 onto the stack here. Remember, 0x01, anything other than 0 is considered true. 0 is considered false. So since the horse has been fed within 1 day, we want to jump to this return true and return true. We could have also duplicated this. There's a whole bunch of different ways we could do that. Now we want to check if it's equal. And remember, if these are equal, it'll be 1. Otherwise, it'll be 0. So on our stack already, for checking if it's equal, it's already going to be correct, right? Like if they are equal, true, that's good. We want that. If not, it'll be false. So we can actually just create another jump destination down here. Oops. Jump destination down here and just jump to it no matter what. So start return 0x00 m store. So this is how we'll store into memory, and then 0x20, 0x00 return. So a little bit confusing, but basically if it ended up being true, we're not going to check if stuff is equal. We're just going to jump to start return true. We're going to add 0x01 so that we store true into memory and we return true. Otherwise, we're just going to have this in here. We're going to skip over start return true, and what's going to be in the stack is going to be this. So if they're not equal, this is going to be false, and we'll return false, and that's exactly what we want. And when we run a test for this, you'll see that this works, but feel free to come back, play with it, and try to mess it up. All right, cool. So is happy horse is done. Hopefully it works right. We'll see when we run the tests. Feed horse is done. By the way, yes, we know feeding unminted horse is currently allowed. I didn't want to have to give you the extra work of blocking that, but we have not minted a horse. We haven't done the constructor. And did we do this one? And we haven't done that one as well. So let's do that one. This one's super easy to do. We just need to make a public macro for that. We just need to make a macro to return that. So define macro horse happy if fed within equals takes 0, returns 0. This one's really easy. We just do horse happy if fed within const 0x00 m store 0x20 0x00 return. So we're going to get this value right here and then just straight up return that. Cool. And that's all we have to do for that one. All right, now we're going to get to the hard stuff here. The minting and the constructor. Let's start with the minting here. So although you'll find the minting is actually not that bad once we get some of the ERC20 functions in here. So we're going to create a new define macro mint horse. It's going to take 0. It's going to return 0 as well. And how does this work? Well, okay, we're going to mint the user a horse with an ERC20 token ID equivalent to whatever the current total supply is. And of course, once we mint the horse, we're going to have to increment the total supply. So one of the first things that we're going to need is the total supply. Well, where do we get that? And this, again, is where our good friends at Huffmate actually have all of this for us. However, I will say that working with the ERC 721, Huff isn't perfect at the moment. So I'm actually going to cheat a little bit by, instead of doing an import here, I'm actually going to do some copy pasting. I know, sacrilegious, but it's okay. So we are going to import a few things. First, we are going to import this common errors.huff, and we're just going to update this code base so that it's ERC20'd up. So lib/huffmate/utils common errors.huff. We're also going to import everything in here from nonpayable.huff to avoid some not so pleasant collisions and imports. So we're just going to straight up copy paste this at the bottom of our contract. Cool. We're going to copy this entire interface here and all the events and all the storage slots and the immutable offsets and the ERC20 constructor. And we're just going to copy everything else. And what we're going to do is at the bottom, once again, we're just going to paste. We're going to paste the whole thing. And let's put a little, well, not a little, let's put a really big comment here saying we got these from Huffmate. Imported from Huffmate. And let's make sure this compiles. Huffc /src horse store v2 store.huff file not found src utils. Let's try it now. Okay, cool. Horse fed happy within. It looks like I named horse fed times location horse fed happy within horse happy fed within. Sorry, that's what I needed to name it, so I renamed it that. And cool, looks like it's compiling. Nice, that was pretty easy. But so now that we've imported it all, well, imported in quotes a little bit there. Now that we've inherited all the ERC 721 functions, we can now get the total supply, no problem, right? Because we can actually work with all the ERC 721 stuff. And even though I just said we need all the ERC 721 stuff, I forgot that that implementation doesn't have a total supply. So we're going to create our own. Define constant total supply equals free storage pointer this. So the first thing we're going to need to do is we're going to need to get the total supply, like so, total supply. And we're going to need to mint, and we're going to need to load sload total supply. So now we have the total supply. So the total supply location, sload it. Now we have the total supply. I'm going to do a dupe 1 here. Just trust me that this will be good. This will work out. And then what do we need to do when we do the mint? Well, we got to safe mint it to the message.sender. So we're going to need to get the message.sender. To get the message.sender, there is a caller opcode, which gets the current caller address. So we're going to do caller, which will give us the message.sender, total supply. Then here's why we imported all this. Then we can call the mint macro, which takes 2 off the stack and returns 0. So input on the stack is going to be the 2 and the token ID. Output on the stack is the nothing. So if we go back up to our mint function, we can see, where did I put the mint function? We have the 2 and the token ID on our stack right now. So we can just call the mint macro. And now we just have the total supply on the stack. So this is why we duped 1 over here, by the way, so that we can have the total supply here on the stack. So now that we've minted, now we want to increment the total supply. So we're going to increment it by 1. So we're going to do 0x01, which will be, which will be 1 total supply. We are then going to do add, which is going to do total supply plus 1. Then we're going to get the total supply location, and we're going to do an store. Pretty much it. So we're going to take this total supply plus 1 value, stick it into the total supply storage location, and then stop. And that's it. And that's our mint function. So I said it was going to be hard, but it's actually real simple because we have this mint macro that came from the ERC721 Huff mate, which pretty much does a lot of the event hashing, logging, invalid opcode, unauthorized, etc. It handles most of the stuff for us so that we can just focus on our horses. So cool. We now have the mint horse done. Now, the only thing we do not have done is our constructor is still not done. So with our ERC721, there's an ERC721 constructor, which I'm not going to go over this. It basically sets up the ERC721 stuff. But what we can do, pretty similar to what we do in Solidity already, is we can say define macro constructor equals takes 0, returns 0, ERC721 constructor, and that's it. Now, because we have the constructor set up like this, we're actually going to need to deploy this a little bit differently than we normally do. So if we go back to our test, I've already kind of set this up for you, so you don't have to worry about this. But the way that we actually deploy this is we do this huffdeployer.config with args, and we add the NFT name and NFT symbol. So this is how you deploy a Huff contract where the constructor has args. And like I said, I've already set that up for you, so you can ignore that. So we're almost done. We're not quite done yet, but if we scroll down into our function dispatcher, we only have our horse store function dispatches. We do not have the rest of our function dispatches, right? We don't have approve or transfer or anything like that. And for this one, once again, guess what we're going to do? We're going to cheat just a little bit. There is an ERC721 wrapper.huff that I'm actually going to cheat, and I'm going to grab. What I'm going to do is I'm actually going to come in here, and I'm just going to copy all the function dispatches from here and copy all the jump stuff. Boop. So once again, we're cheating a little bit, and we're going to put this in our function dispatcher. Yay. So let me go find the main function, and we're going to have to do a little copy paste fun here. Paste. Okay, cool. Looks good. Let's copy this. We need to put these below all of the dispatches down here. Boom, like this. Revert on a failed dispatch. Okay, those all look good. Cool. Let's try to compile this. The Huff C. Oh, we're missing macros safe mint. I believe those macros are in here. I think so. Yep, safe mint with data and safe mint. So we're going to copy these last macros, stick them right at the bottom, and try to compile this again. We're missing the mint macro mint. Oh, is that in the wrapper too? Oh yeah, sure enough. Burn and mint were in the wrapper. So we're going to paste those two. And boom, it's compiling. So I think we're done here. Now I know we did a lot of copy paste. We did a little bit of cheating here, but this should essentially be our ERC721 horse store v2 in Huff. Let's try running some tests. Forge test. Pass. And okay, we got some fails. Let's see why we got some fails. Let's run this one. Forge test -mt. Paste that in. 4 V's. See what happened. What did we forget? EVM error revert. Okay, why did we revert? Looks like total supply static call reverted. Do we have a total supply? We forgot to add a total supply interface. Do we have a total supply? We don't have. Okay, we need a total supply function dispatcher here and a total supply function. So let's do define macro total supply, takes 0, returns 0. This is going to be pretty simple here. We're just going to grab the total supply pointer. We're going to s load it, 0x00 mstore, and then we're going to do 0x20, 0x00 return. And then I think that should be it. And we need a function and we have a function dispatcher. We need to add, copy paste this, total supply, and we need to add it to the interface. Total supply turns you into 256. I think that looks good to me. Let's try compiling it and let's try testing it. I think we should be pretty good. Maybe I'm being, hey, we do look pretty good. Okay, forge, test, and everything passes. So now that everything is passing, one of the coolest things we can do in Foundry is we can do forge snapshot. And this will run all of our tests, but it'll also keep track of all the gas associated with it. So I just ran forge snapshot, and now I have this .gas snapshot file here where we see horse store v2, horse store sulk, horse store v2, and we can do some comparisons in here of the different Huff versus Solidity. So I'm going to do a little copy pasting here where we have horse store sulk, and one of these is Yule. I don't know which one, but we can compare. Okay, horse store Huff versus sulk. So horse store Huff 7419, horse store sulk 7525, or it looks like this one's a fuzz. So this is what, test read value? Oh, these are both test read value. Boom, boom, boom. So it looks like Huff by far is more efficient than Solidity and Solidity Yule. Okay, well, what about test write value? Okay, so we have these kind of being the two values. Maybe this is the lower, this one of these is the average or the highest or the lowest. I forget, but it looks like even these two values in Huff are more gas efficient than that in Solidity or Solidity and Yule. Okay, let's keep going down. What about horse store v2? Okay, test feeding is 106,119 versus in Solidity is, oh my goodness, it's almost 10,000 more gas to do it in raw Solidity than raw Huff. And you can see why it could be such a good idea to code your smart contracts in Huff or in lower level programming languages, because you can get them so much more gas efficient. But keep in mind, we did remove a lot of the safety that we probably shouldn't have, right? We didn't check for message.value. We didn't check for call data. We didn't check for call data size. There were all these checks that we skipped out on the Huff, which of course are going to make it more gas efficient, but might not be best practices. Some areas that don't need that level of security, like for example, returning the name, yeah, this would be a great improvement to have in your smart contracts. Look, it's almost 2,000-3,000 gas cheaper in Huff than Solidity here. We have successfully written a horse store v2 with mappings with ERC20s in Huff in very low level, essentially binary bytecodes here. This is hard stuff. And the fact that you got this far, you completed section 1 of the EVM assembly and opcodes course. This is incredibly exciting. Now I know because you've gotten this far, you're obviously no slouch, right? You know a lot about the EVM, you know a lot about Foundry, you know a lot about Solidity, you know a lot about smart contract development, and you just got that much better. So with this, you've actually completed section 1 of the EVM assembly and formal verification course. Give yourself a pat on the back. Now's a great time to go get a coffee, go get an ice cream, go to the gym, but take a break. But before we take a break, we're going to do a quick recap of everything we learned in this whole section, and then especially what we just did. So, quick recap. So what did we learn in this section? Well, we learned about a lot of stuff. Even though we probably already knew this, we learned about how the stack and memory work in Solidity. We have a stack, we have memory. When we push stuff onto the stack, we can use the mstore to then store it onto this array called memory. We learned that in Solidity, we have this thing called the free memory pointer, which points to this spot in memory where it says, hey, there's nothing here. And every time it gets updated, we update this free memory pointer. We learned that we can take a smart contract written in Solidity and break it down to the most atomic of its matter. And we learned a great way to write with the Huff programming language. And we learned how to write some smart contracts in Huff. And we learned that if we wanted to write incredibly gas efficient smart contracts, Huff would be a great way to do this, or Huff is just a great way to learn this low-level EVM. We additionally learned about Yule, where we can do inline assembly in our smart contracts to make them much more gas efficient, or just to have access to lower level code. And with Yule, we learned that you can write inline assembly, but you can also write an entire smart contract completely in Yule or assembly. When it came to our testing, we already learned some clever ways to do differential tests, where two of the same code bases get tested on the exact same code. So we tested our Huff, our Solidity, and Yule all on the exact same tests with very minimal changes to our testing suite. We learned what every single opcode in one smart contract does, and we learned how to do some stack-looking syntax for comments when we're reading opcodes. And we learned how to read opcodes and tell exactly what a smart contract is doing. We learned about a lot of different opcodes and what they do, and we learned about the EVM.code's playground, which is a great place we can play around with opcodes. Another place we can play around with opcodes is going to be the Foundry debugger. We can run forge test --debug and then a test name, and it'll drop us into a debugger where we can go opcode by opcode through any transaction in Foundry. We learned more about building an even more advanced smart contract. We learned that Huff can do imports. And most importantly, we learned how to work with mappings in Huff, or mappings at the lowest level. We got a little bit more comfortable with jump destinations and jumping around. We got pretty comfortable with using the Huffmate to work with keys and work with data. And we built a much, much more complicated Huff smart contract using an ERC721 and this horse thing. And even with the horse thing, we didn't go through this together, but we took that same methodology of doing differential tests with Huff and Solidity, and we applied it to our horse store V2, which was much, much more complex. And still, we were able to find that these two smart contracts were equivalent essentially in their functionality. We learned that smart contracts are separated into contract creation code, runtime code, and metadata. And we learned that if ever we run into a scenario where life or death, we have to tell somebody what a lump of binary does, we can do it. There's going to be times where attackers do not verify their attacking smart contracts. And if it's important enough, guess what? What we can do is even we can break down what those smart contracts have done, what the binary represents, and convert it back to Solidity. There are some disassemblers or decompilers that try to do this for us, but they can be a little rough around the edges. So you now know how to do it manually. We learned about the free memory pointer in Solidity, which is incredibly important. And this will come up even more when we talk about Viper, or if you ever get to Viper. So we learned an absolute massive amount here. And you might still not feel super comfortable with opcodes. That's okay. What I will say though, is a lot of smart contracts are not written in Huff, right? It's too hard to write in Huff. However, there are a lot of smart contracts written with a lot of assembly. And we are going to get more comfortable with assembly in section 2, because there's going to be a lot of assembly in section 2, Math Master. However, in order to really understand the assembly, you really need to understand the opcodes first. So I think one of the best ways to get good at these opcodes is to keep working with Huff. So now is a great time for you to take a step back and convert a minimal smart contract of your own into Huff or Yule or inline assembly or whatever you want to do. Oh, shit. That's going to make you so much more comfortable with these opcodes. Huge, huge congrats for getting this far. If you want to go the extra mile, definitely be sure to take this challenge up for yourself. Go get that coffee, go get that ice cream, and we'll see you in the next one. So now that everything is passing, one of the coolest things we can do in Foundry is we can do forge snapshot. And this will run all of our tests, but it'll also keep track of all the gas associated with it. So I just ran forge snapshot, and now I have this .gas snapshot file here where we see horse store v2, horse store sulk, horse store v2, and we can do some comparisons in here of the different Huff versus Solidity. So I'm going to do a little copy pasting here where we have horse store sulk, and one of these is Yule. I don't know which one, but we can compare. Okay, horse store Huff versus sulk. So horse store Huff 7419, horse store sulk 7525, or oh, it looks like this one's a fuzz. So this is what, test read value? Oh, these are both test read value. Boom, boom, boom. So it looks like Huff by far is more efficient than Solidity and Solidity Yule. Okay, well, what about test write value? Okay, so we have these kind of being the two values. Maybe this is the lower, this one of these is the average or the highest or the lowest. I forget, but it looks like even these two values in Huff are more gas efficient than that in Solidity or Solidity and Yule. Okay, let's keep going down. What about horse store V2? Okay, test feeding is 106,119 versus in Solidity is, oh my goodness, it's almost 10,000 more gas to do it in raw Solidity than raw Huff. And you can see why it could be such a good idea to code your smart contracts in Huff or in lower level programming languages, because you can get them so much more gas efficient. But keep in mind, we did remove a lot of the safety that we probably shouldn't have, right? We didn't check for message.value. We didn't check for call data. We didn't check for call data size. There were all these checks that we skipped out on the Huff, which of course are going to make it more gas efficient, but might not be best practices. Some areas that don't need that level of security, like for example, returning the name, yeah, this would be a great improvement to have in your smart contracts. Look at it, it's almost 2,000-3,000 gas cheaper in Huff than Solidity here. Now, Forge has a great debugger. Tenderly is another debugger we talked about a little bit in the security course. It can do some of the same opcode by opcode debugging, which is absolutely fantastic. And then additionally, we talk about this a little bit in the wallet course. There's this phenomenal tool called MetaDeck. It's a Chrome extension. And if you get it, what will happen is if you go to like Arbitrum Scan or Etherscan or anything like that, it'll give you this little risk, fund flow, and these little tags up here. It'll give you some more context on who funded the contract. It'll give you little buttons where it'll bring you over to the DDoB website where you can actually try to decompile it, see what's in storage, etc. And just adds a whole bunch of nice little pop-ups when you're working with Etherscan-like explorers. So really good tools. So take that break, get that coffee, because we're going to go even deeper into assembly, and we're going to finally get introduced to formal verification and symbolic execution. Go get that coffee, go get that ice cream, go hit 315 on the bench at the gym, and I'll see you in a bit.